Why? People have always asked the big questions. How was the universe created? Why does it work the way it does? Why do we find ourselves on this tiny planet, buzzing with life? Looking at the really big picture revealed unexpected connections. If you want to know about humanity, you have to ask about the whole universe. These questions fascinated me even when I was a kid, because they made me feel I was part of something absolutely huge and quite wondrous, and I wanted to know more about it. I began teaching a history course that began with the Big Bang, 13.7 billion years ago. I called it Big History.
Big History is my favorite course of all time. It blurs the boundaries between science and geography and history and literally tells the story of the universe. David Christian made it so intriguing. I loved his course and wanted to talk to him about how can we make this available to more people.
Together, we're creating a free, online and in-class course for high school students.
Big History is the first class that I can actually say I've enjoyed history in.
You study this huge spectrum of history.
Like looking at the different theories that different people have had.
It's the history of everything on a very broad scale.
That it's more than just this textbook that's static.
Whenever I go to class, I really enjoy the discussions that we have.
It's just made me feel a lot better about school generally.
By the end of this course, you'll have surveyed the whole history of the universe, and you'll know how you fit into it. So let's get started.
Eight dramatic transitions drive Big History's 13.7 billion year story. We call these major thresholds of increasing complexity. They're times when the right ingredients combined with just the right conditions to enable the creation of an entirely new form of complexity. When our universe appeared, it was simple and, from our perspective, frankly, a bit boring. There were no stars, no planets, no life, and certainly no humans. And yet, look around, and you'll see amazing complexity. A sky filled with stars and galaxies in all stages of development. You'll see a solar system formed by the remnants of stars that were born and died billions of years ago. You'll see our own Earth filled with mountains and rivers, deep caverns and vast oceans, and incredible biodiversity. And you'll see our own innovative species with our computers, airplanes and skyscrapers, and our endless art and invention. 8 thresholds explain how a relatively simple universe transformed into the rich complexity that's all around us today. Each threshold builds upon the previous one. Together, they help explain where everything came from. They help explain our own place in the universe and where things may be heading. Today, much of the universe is still pretty simple, with large tracts of empty space. We'll see how complex things appeared in special regions where the ingredients and the Goldilocks conditions were just right to cross new thresholds of complexity. Step by step, we'll see how new forms of complexity appeared, each with components and qualities that had never been seen before, leading to the world we live in today. Our first threshold is the Big Bang, which happened about 13.7 billion years ago and led to the creation of the entire universe. We don't know much about the ingredients and the Goldilocks conditions that led to this first threshold because we just don't have much evidence. For example, what made the Big Bang possible? We don't know. Why did the Big Bang happen? We can only speculate. Was there even space and time before the Big Bang? We don't know that either. What we do know is that the Big Bang provided the raw materials for everything around us today. After the Big Bang, there was space, which was rapidly expanding, and there was time. There was also matter and energy. At first, the universe was so hot that you couldn't tell the difference between matter and energy. But within the first billionth of a second after the Big Bang, matter and energy separated. Then, energy took different forms, including gravity and electromagnetism. And matter appeared in the form of electrons and quarks soon linked up to form protons and neutrons. Why is this so important? Because nothing had turned into something. And that something contained everything needed to build an interesting universe, one that could eventually include you and me. Now let's take a closer look at how our universe began to build more complex things. Right after the Big Bang, our young universe was what scientists call a plasma. This was basically an incredibly hot mush of charged particles without much structure or complexity. About 380,000 years later, things began to change. By then, temperatures had fallen low enough for protons, which have positive charges, to link up with electrons, which have negative charges, and together they formed electrically neutral atoms, very simple ones like hydrogen, some helium, and a few slightly heavier atoms thrown in for good measure. The universe now contained vast clouds of these atoms. Add gravity, and now you have the ingredients for our second threshold, the formation of stars. Here's what happened next. Wherever there is slightly more matter, gravity is more powerful. So tiny variations in the density of matter became the first Goldilocks condition for this second threshold. Gravity packed slightly denser regions ever closer together, squashing them so tightly that they began to heat up. This growing pressure and heat created our second Goldilocks condition. Eventually the clouds got so hot that protons and electrons split apart once more, recreating a plasma. And when temperatures in these hot spots got to about 10 million degrees Celsius, protons began to fuse together. And part of them turned into energy as they did so. This huge release of heat from the center of each cloud of matter stopped the cloud from collapsing any further. And this is how the first stars lit up. Soon, the universe had billions of hot spots, pouring energy into the cold of deep space. Each star would continue releasing energy into space for millions or even billions of years, until it had no more protons to fuse. And as these stars formed, so did galaxies, each containing billions of stars. Galaxies, in turn, grouped together into huge clusters and chains of galaxies, the largest structures in the universe. Suddenly, the universe seemed to have a lot more variety and a lot more structure. Now, what new things could happen in a universe filled with stars?
Hi, I'm John Green, and this is Crash Course Big History. Today we're going to be exploring what happened to the universe after the Big Bang, particularly how you and I and everyone you know emerged from stars. And we'll also be investigating the burning question of why anyone who studies history has to care about chemistry. Mr. Green, I'm sorry, but I hate chemistry. Why can't we just learn about, like, English kings stabbing each other? Sorry, me from the past. The thing is, if you look far back enough in your family tree, you're going to find not just, like, farmers and foragers and fish and microbes, you're gonna find stars. And I don't mean stars like Kim Kardashian, who is actually not a star. She is a person. I mean actual stars, me from the past. And to understand how we got from stars to people, you're gonna need some chemistry. So last episode, we went from the very beginning of everything to the release of cosmic background radiation, and CBR is a major piece of evidence that the Big Bang happened. Studying it closely also tells us the age of the universe, and it allows us to see the minute variations in temperature and density of the early universe, and it turns out that those tiny differences are a really big deal. So when the universe inflated from much, much smaller than an atom to the size of a grapefruit in a split second, there were quantum fluctuations, tiny little blips on the unpredictable quantum scale, and they created those little variations that we see in cosmic background radiation. And as the universe continued to expand, I mean, it is currently larger than a grapefruit, those variations in density were inflated to such a scale that gravity was able to take hold and start clumping together clouds of hydrogen and helium gas. So 380,000 years after the Big Bang, the universe was becoming an increasingly cold and increasingly boring place. Like, temperatures were no longer high enough to forge new elements, and if hydrogen and helium hadn't clumped together, nothing would have ever happened ever again. Our universe would just be a dull, homogeneous place with some clouds of hydrogen and helium gas floating around. Dull and gassy. Just like North Dakota. I'm just kidding, North Dakota. You do have a lot of natural gas, but you're very interesting. I mean, you have Mount Rushmore. What's that? Oh, I see. All right, sorry. Yeah, then, But what happened is that while the universe on the whole continued to cool, thanks to those tiny variations that emerged during inflation, certain pockets of the universe were about to get very hot.
Indeed, a liberal dose of hot sauce was yet to come. Hydrogen and helium, though, are light gases. They are the lightest two elements, so light that they require very little encouragement to escape the Earth's atmosphere. But while the explosive force of the Big Bang flings matter and energy apart, gravity has the ability to pull tiny pockets of the cosmos back together, provided it has some wrinkles in the universe to work with. As gravity sucked hydrogen and helium atoms together, enormous thick clouds began to form. While the expansion of the universe continued to increase the gaps between these clouds, the density of these pockets also increased. The vastness of empty space began to be filled with tiny islands where atoms of hydrogen and helium were increasingly squished together. Despite being the lightest of all the elements, the immense amount of all that gas built pressure up in the center. Increasing pressure meant increasing temperatures. Just like after your 2 a.m. taco run, suddenly these gassy pockets were burning inside. It was in this rather uncomfortable state of heartburn that the first stars flared into life, roughly 100 million years after the Big Bang. By a billion years after the Big Bang, the universe was starting to look like what we think of as a universe, an immense vastness littered with hundreds of billions of galactic islands containing hundreds of billions of stars. And as recent work with the Kepler Space Telescope has revealed, a mind-numbing number of planets.
So the universe is big. It's really big, but it's not so big that it's impossible for the average person to get a mental picture of, like, our neighborhood. Our galaxy, the Milky Way, formed from these galactic mergers with other galaxies that stopped, like, around 10 billion years ago. Our galaxy is about 100,000 light years across, which means that it takes, 100,000 years for light to get across it. And even if humans become, like, technologically capable of colonizing the galaxy in the next millions of years, our little galactic island is probably where we're gonna stay, just peeping out on the rest of the universe. So there are between 200 and 400 billion stars in the Milky Way with huge distances between them. And there hasn't been a merger between our galaxy and another for a long time, but our neighbor Andromeda, which has closer to 1 trillion stars, is actually set to collide with us in 3.75 billion years. But don't worry, this isn't going to be like a car crash, because the vast distances between stars make it very unlikely that stars will actually hit each other in such an event, although many new stars will form. Instead of a car crash, think of like a 3 billion year long tango of two graceful galactic dancers. This is going to totally mess up the constellations that we're familiar with now, but the good news is that by that time the sun will have wiped out life on Earth regardless, so we won't have to worry about it. And the even better news is that, let's face it, there's no way our species is making it until the sun wipes us out. As far as these galactic islands go, ours is a modest size. Like, Malin 1 is a spiral galaxy like ours, but it's a whopping 680,000 light years across. across. And the giant elliptical galaxy, excitingly named M87 because astronomers are so good at naming things, is 980,000 light years across. And with its radio jets, the elliptical galaxy Hercules A, that's a slightly better name, is a whopping 1.5 million light years across from end to end. Galactic islands are separated by millions and millions of light years, and the Virgo supercluster of galaxies, to which the Milky Way belongs, is roughly 110 million light years in diameter, and that's only one of many, likely infinite superclusters in the universe. Wait, literally infinite? Wow! Unfortunately, we can't know whether the universe truly is infinite or not because of a little thing called the cosmic horizon. We can only see the light that has reached us from the start of the universe 13.8 billion years ago. Simply looking into the sky is an act of investigating history, and the farther we look back, we begin to see more primitive things, the first stars and galaxies. Mind you, the light we observe billions of years after it first shone and the continued expansion of the universe means that the cosmic horizon is approximately 46 billion light years away by now. Roughly double that, and you know that our little cosmic bubble is about 92 billion light years across. I mean, compare that to our already huge 100,000 light year galaxy. Just for a little bit of context, the circumference of the Earth is less than 1/5 of 1 light second. But beyond our little cosmic bubble, there is more universe eternally inflating, and where our universe is sort of one hole in a block of Swiss cheese, other holes might exist in that block of cheese, multiple universes with laws of physics completely different from ours. What? I know, right? It's nuts! It's actually more like cheese, but it's nuts! But our cosmic bubble, while it's very large, is not such an intimidating place. Like, it's pretty easy just to get a mental picture of it. A vast bubble with a lot of empty space and a light dusting of galaxies. To further this point, and don't take this too seriously, but in 2002, Carl Glazebrook and Ivan Baldry added up the light from 200,000 galaxies and determined that if you were able to stand outside our cosmic bubble and look at it with human eyes, the color of our universe would be, wait for it, beige. That's a bit of an anticlimax, so they tried to dress it up by calling it Cosmic Latte. But I don't mind beige. I mean, look, this stuff is gigantic and somewhat scary, but you can't be scared of beige. And a lot of cosmologists infuse their lessons with a sense of awe at this vast expanse, and that awe is certainly justified. I mean, the universe is literally awesome. But let me ask you this. If you lived in New York City, would you feel bashful or depressed about the size of your city compared to, say, the miles and miles of the plains of Saskatchewan? So yeah, there are millions and millions of light years of empty space. But it's empty space. One thing we find out about the rising complexity in big history is just how unique some of these tiny areas of the universe can be. This is where the action is.
Enough of the pontification. Let's get back to those gassy, heartburn-suffering stars. As core regions of the gas clouds heat up, the atoms get jumpy, move faster and faster, and collide with ever-increasing ferocity. Eventually, it's ferocious enough to overcome the electric repulsion between the atoms. They fuse, and the cloud officially becomes a star. Hydrogen atoms fuse into helium atoms at about 10 million degrees, releasing yet more energy. The sun is a massive hydrogen bomb in the sky, and the release of energy in just the right amounts is very good for us, provided we don't mess up the ozone layer too bad or spend too much time tanning on the beach. When it comes to stars, size matters. If an initial cloud is smaller than 8% of the size of our sun, it'll never form a star, maybe only a brown dwarf. If the initial cloud is 60 to 100 times our sun, it will probably split into 2 or more regions of stellar formation. If the cloud is between 8% and 8 times the size of our sun, it has a longer lifespan. Our sun is middle-aged and will last for about another 5 billion years. Much smaller stars may have lifespans of hundreds of billions of years. Large stars sometimes only live for a few 100 million years. As all stars run out of hydrogen and helium as fuel, the outer edges of the star swells up. Fusion of heavier elements occurs, requiring higher and higher temperatures, creating heavier and heavier elements, all the way up to iron. But elements heavier than iron can't be created in stars. There simply isn't enough energy to fuse those heavier nuclei together. So how is the rest of the periodic table formed? When giant stars, 8 to 60 times the size of our sun, exhaust their fuel, they collapse. element. This may last no longer than a second, but it will be followed by a huge explosion. These explosions shine with the energy of billions of stars, and combined with proton and neutron capture, supernovae are responsible for creating the heavier elements of the periodic table. Flinging out these elements, the rest of the cosmos is fertilized and nourished by the ashes of dead stars.
Carl Sagan said it best: we are made of star stuff. And he really meant that. I mean, you see this globe? It was made in the belly of a star. You see your computer? Made in the belly of a star. Your dog? Made in the belly of a star. Your right hand? Made in the belly of a star. Your left hand? Potentially made in the belly of a different star. Stellar evolution bridges the gap between the mind-boggling origin of our universe and the tangible material stuff that you see around you, and in fact, the tangible material stuff that you are. Humans haven't just appeared out of nowhere. We've changed form. We used to be much hotter, of course. I mean, temperature-wise. This is why chemistry is important to understanding the grand narrative of 13.8 billion years, and it's also why we look at the big history of individual objects, something we call little big history. Like, see this ring on my finger? I bought it in a jewelry store. A nice person sold it to me. A jeweler crafted it, and miners dug it out of the ground. But it got there by being flung out of a huge star in a massive explosion billions of years ago. It wound up in our solar system, was part of the tiny 0.1% of matter that didn't get sucked into the sun, accreted from the dusty debris in the one sliver of the solar system where the Earth was, and because gold is an iron-loving element, it was more prone to sink to the center of the Earth, making it even more unlikely that it should be found on the Earth's crust. Rare and shiny things are valued by a lot of human social orders, and during the agrarian era, gold became a sign of social standing and wealth, and in marriage tradition, giving someone an expensive gift can be a sign of esteem. Hence, Sarah and I spent $450 on this, which we could have spent on an Xbox.
Tiny wrinkles in the early universe had a major impact on one of the unifying themes of 13.8 billion years: rising complexity. Wrinkles created stars, stars created elements, and some of those elements came together to form life and, of course, us. Gradually, we see an increase in the number of connections and building blocks present in the universe. For instance, a star is comprised primarily of two elements, hydrogen and helium. But here's the thing. If there had been no wrinkles in the early universe, energy would have been evenly distributed across the cosmos. Without flow of energy, like say that through a star, no complexity can arise, none whatsoever. This state of existence is called thermodynamic disequilibrium, which means that energy is not evenly distributed. A simple structure like a star is big, but it's just a large pile of the lightest elements and doesn't score very high in energy flow density. Your brain is 75,000 times more complex than a similar sized chunk of the sun. Its building blocks and nodes are way more intricate. Your brain has way more connections than there are stars in the galaxy. You wouldn't think a story that spans cosmology, geology, biology, and human history would have a unifying theme, but rising complexity is something that stretches across all 13.8 billion years. And it began with those tiny wrinkles in the early cosmos.
So now moving past, I hope you see why a basic understanding of chemistry is important to understanding our ancestry. I mean, stars are pretty much your great-great-great-great-great-great-great-great-great-great-great, etc. grandparents. And you wouldn't ignore your grandparents, would you? Mr. Green, no way. I mean, they're a big part of my plan to get a car for my 16th birthday. That's really touching me from the past. Also, I've got bad news for you. So in today's episode, we've learned that everything around us, everything that we can touch and feel and see, even us, is debris floating around enormous stars in the vacuum of space. We clump into specks, we change form, but we owe our entire existence to these burning, gassy balls that we see in the night sky. We may just be the ashes of dead stars, but those ashes hold the potential to arrange themselves in increasingly complex ways, from which the Earth and all it contains can arise. But more on that next time.
After Threshold 2, the universe had lots of stars, but most of space was still cold, dark, and mostly empty. The universe consisted almost entirely of two types of atomic matter, hydrogen and helium. These were both light gases, and one of them was totally inert. Like a painter with just two colours, one of which won't mix, it was impossible to make anything very interesting. The universe needed more colours, more chemical elements, and that was the work of Threshold 3. Making new elements meant fusing more protons and neutrons together. To do that, you needed very high temperatures, which could only be found inside massive stars that were aging or dying. Only they have the right Goldilocks conditions for threshold 3. Why? Well, large stars have so much mass that they can create enormous pressures and temperatures. Those temperatures get cranked even higher when large stars run out of hydrogen. When that happens, fusion stops at the center and the star collapses like a burst balloon. If the star's big enough, the collapse is huge, creating such high temperatures that helium nuclei can fuse into nuclei of carbon. When the star's used up its helium, it collapses again, and the cycle starts over. The star heats up and starts to fuse carbon to form oxygen. It collapses again, then does the same to create other elements like silicon, nitrogen, and eventually iron. If it's a really, really big star, it'll finally die in what's called a supernova. That's an explosion so hot and so energetic that, for a while, it'll shine like an entire galaxy, and it'll produce enough heat to form all the other elements of the periodic table. Then the supernova scatters these new elements into space, and voila! We have a universe with lots of different elements. Threshold 3 was crossed for the first time when the first large star died. And it's still being crossed today, as billions upon billions of large stars die, scattering the raw materials needed to build wondrous new forms of complexity.
Hello, I'm Hank Green. Welcome to Crash Course Chemistry. Today, we're talking about the most important table ever. Not the table where they signed the Declaration of Independence, nor any table of contents, nor this table right here, nor the stone table of Aslan. Nay, it is the periodic table of elements, a concise, information-dense catalog of all of the different sorts of atoms in the universe. Today, I want to talk a bit about the creation of this table, which is, to be clear, one of the crowning achievements of human thought. To start out, though, let's close our eyes and pretend. Imagine you're in Siberia, and you're a 13-year-old boy, and your father, who was a professor but had gone blind, leaving your family of more than 10 brothers and sisters destitute, has just died. I know, downer. Your mom, to support the family, has reopened an abandoned glass-making factory in the small town where you live, largely because she wants to make enough money to send you to school someday. A year passes, the factory burns down. But your mom, she sees your potential. She knows that you have a keen scientific mind and will not see that squandered. So, with your siblings out of the house and on their own, she packs up your belongings, straps them to a horse, and with you in tow, rides 1,200 miles through the Ural Mountains on horseback to a university in Moscow. There, on your behalf, she pleads earnestly and effectively, and they reject you. So together, you ride another 400 miles to St. Petersburg, to the school where your father graduated as a scientist, and as luck, or extreme, insane, undeniably Russian persistence would have it, they accept you, and your saddle-worn butt, as a pupil. Your mother, having completed her mission, promptly dies. If you're doing your imagining as I've told you, you might feel a tremendous debt to your mother and a very deep desire to ensure that you achieve something on par with the sacrifices she made for you. And maybe that's one reason why Dmitri Ivanovich Mendeleev became the crown jewel of Russian science and a theorist who revolutionized how we see the world. Mendeleev spent a great deal of time in laboratories as a student, studying the burgeoning new field of chemistry. He worked with all the elements that you could work with at the time, and his knowledge gave him unique insights into their properties. Those insights would come in handy. Let's all imagine we're Mendeleev again. I like doing that. And that we know a bunch of stuff about chemistry, which, you don't yet. but we're imagining. So it's the 1860s, and about 60 elements are known to mankind, and their atomic weights are mostly known as well. So the simplest thing was just to sort them in order of their atomic weights. But interestingly, you, because you're clever pants, realized that the most significant relationships seem to have nothing to do with the atomic weight. Lithium, sodium, potassium, and rubidium were all extremely prone to reacting with chlorine, fluorine, iodine, and bromine. Beryllium, magnesium, calcium, and strontium were all similar but less reactive. But with a quick inspection, you, and to be fair, a number of other chemists, realized that there was a relationship between atomic weights, but it's periodic. At the beginning of the list of elements, characteristics repeat every 7 elements. On a side here, we now know that it's every 8 elements, but in the 1860s, elements were studied based on their reactivity, so the non-reactive noble gases had not yet been discovered, so the period occurred every 7 elements. As the mass of the elements increases, the repetition starts to look a little less periodic, though it's certainly still there, it just isn't perfect. Some of your colleagues, they're saying, well, such is life. It was perfect repetition early on, but later in the list it gets a little fuzzier. But not you. You become obsessed. Obsessed with the perfection of the periodicity. You write out the names and weights and properties of elements on cards, you lay them across your desk, shuffle them, tear them to pieces in frustration until one day you realize that you're simply missing cards. The numbers aren't working, not because there's something wrong with your ideas, but because some elements simply haven't been discovered yet. Armed with this insight, you insert gaps into the table, and things suddenly fall perfectly into place. 7 element periods for the first 2 rows with hydrogen in its own category, 18 element periods for the next 2 rows. You're so certain that you predict the properties of these missing elements, and when a French scientist comes along and says that he has in fact discovered one of them, you argue with him, saying that you discovered it first in your mind. And when you see his data, and it doesn't match yours, you publish a paper saying his data for the new element he discovered is wrong. That's how certain you are of yourself and this beautiful new theoretical framework you've created. And you know what the really crazy thing is? You're right. That French guy's data was wrong. You, never having examined the element he discovered, knew more about it than he did. Because you are Mendeleev, master of the elements. Okay, we're done imagining for the episode. That was fun, though. The different groups Mendeleev had identified are a lot of the same groups that we study today. Starting at the left, we have the soft, shiny, extremely reactive alkali metals. So reactive, in fact, that they have to be stored in inert gases or oil to prevent them from reacting with the atmosphere. Alkali metals want nothing more than to dump off an electron and form a positive ion or cation. And they're always jonesing to hook up with a hottie from the other side of the table. So of course, seeing as they're so reactive, you don't find hunks of them lying around in nature. Instead, chemists must extract them from compounds containing them. Next, you have the alkaline earth metals. Reactive metals, but not as reactive as the alkali metals, forming cations with 2 positive charges instead of just 1. Calcium, shown here, undergoes a very similar reaction to sodium and water, just a little more slowly, producing a little less heat. The middle body area of the table is made up of a nice solid rectangle of transition metals. These are the metals you think of as metals, with iron and nickel and gold and platinum. The majority of elements are metals. They're fairly unreactive, great conductors of heat, but more importantly for us, good conductors of electricity. They're malleable and can be bent and formed and hammered into sheets, and they're extremely important in chemistry, but overall surprisingly similar to each other. On the far right, just over from the noble gases, the halogens make up a set of extremely reactive gases that form negative ions, or anions with 1 negative charge, and love to react with the alkali and alkaline earth metals. The rectangle between the halogens and the transition metals contain a peculiar scattershot of metals, metalloids, gases, and nonmetals. These guys don't end up as ions unless you take extreme action and start shooting other ions at them, so generally a bit boring over here, though lots of interesting covalent organic chemistry. We'll get to that. Down below, in their own little island, are the lanthanides and actinides, metals that were largely undiscovered in Mendeleev's day because they're so similar that it's next to impossible to separate them from each other. And finally, on the far, far right, also undiscovered when Mendeleev built his chart, the completely unreactive noble gases. Like a lot of other obsessive scientists, Mendeleev never thought he was done with his table, so he held it back for quite a while, only publishing it as part of a new chemistry textbook he was working on as a way to make some quick cash that he needed. And as with many other scientific revelations, there were a number of other people hot on this discovery's trail. As many as 6 people published on the periodicity of elements at roughly the same time as Mendeleev, but a few things set him apart. One, he was obsessive. He knew the data better than anyone else and had spent a ton of time working on a theory that many people thought was just an interesting little quirk. And two, he realized in a way no one else did that the idea of periodicity had far-reaching consequences. It seems as if he had a deep belief in the cosmic importance of what he was doing, almost a religious fascination. Mendeleev believed in God, but also he believed that organized religions were false paths to the unknowable nature of God. I like to believe that he thought he saw some divine pattern in his tables, and Mendeleev felt as if he was coming to know God in a way that no other man ever had. To be clear, this is pure conjecture. And as we now know, the periodicity of elements is a physical phenomenon. It's a function of electrons, which are in some ways pretty dang peculiar, but certainly not at all mystical. But we'll get to that peculiar physical reality in the next episode. The periodic table that we know and love, I love it anyway, is a representation of reality, a way of understanding and sorting the universe as it exists. But that form of the table is not by any means set in stone. Indeed, a contemporary of Mendeleev envisioned the table set onto a screw or cylinder with the elements wrapping around from one side to another. While Mendeleev's table looks more like a map up on a wall, de Chancourtois, a geologist, envisioned more of a globe. Unfortunately for de Chancourtois, no publisher could figure out how to print his cylindrical three-dimensional table, and so he published his paper without a graphical representation of his periodic cylinder of the elements, and it was largely ignored. I guess they didn't have papercraft back then. I am a huge fan of this cut and tape model of the periodic table. You can make your own, there's a link in the description, and there are also a ton of other designs for periodic tables that have various advantages over the one that we're all familiar with. Our periodic table as it stands is really a little bit unhappy with itself, frankly. The lanthanides and actinides really should be part of the table, but we separate them out because it's hard to fit that on a piece of paper. Really, this is what it should look like. And really, it would be best if it wrapped around into a circle, so that fluorine and neon and sodium were all next to each other, instead of being on the opposite sides of the map, because they're just one proton away. Mendeleev's contribution, nonetheless, is more powerful than at first it seemed. He ended up forming a guide to help future chemists understand things that wouldn't be discovered for 25, 50, even 100 years. Indeed, after Mendeleev's theories were published and accepted, the overwhelming cry from the scientific community was, why? 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 And though Mendeleev was not himself concerned with this stuff, he actually denied the existence of atoms, or indeed anything he couldn't see with his own eyes, it turned out that the answer to the first why was the electron. That sneaky little electron, Mendeleev, if he'd been around to see their discovery, he would have hated them. But you will have a healthy respect for them after you learn all about them on the next episode of Crash Course Chemistry. Thank you for watching this episode of Crash Course Chemistry. If you were paying attention, you now know the terrible, beautiful, and wonderful story of Dmitry Mendeleev, how he organized the elements into the periodic table, some of the basics of the relationships on that table, why Mendeleev stood out from his colleagues, and how the table as we know it today could stand some improvement. This episode of Crash Course Chemistry was written by myself, filmed and directed by Caitlin Hoffmeister, and edited by Nick Jenkins. The script was edited by Blake DePestino and Dr. Heiko Langner. Our sound designer is Michael Aranda, and Thought Cafe is our graphics team. If you have any questions, please ask them in the comments below. Thank you for learning with us here at Crash Course Chemistry.
Today, about 98% of the atomic matter in the universe consists of hydrogen and helium. But thanks to threshold 3, that other 2% is made up of all the other elements in the periodic table. That makes some amazing things possible because these different elements can combine to form an almost infinite number of different types of matter. Objects that are much more complex than stars could now form. Objects like planets. And that was the work of threshold 4. Here's how it works. When new stars are formed, they're surrounded by huge clouds of chemically rich matter, are ingredients for this threshold. These clouds spin in different orbits around the newly forming star, creating Goldilocks conditions that are just right for elements to combine. Some atoms combine chemically to form a variety of different molecules, but also atoms and molecules often clump together to form bigger and bigger lumps of matter. This process is called accretion, and eventually it goes on to form entire planets. Now, since lighter elements are much more plentiful in the universe, many planets consist mainly of hydrogen and helium, like Jupiter and Saturn. But because hydrogen and helium atoms are so light, intense radiation sometimes blasts them away from regions close to the new star. Those regions then contain a relatively high concentration of other, heavier elements, and eventually these elements may clump together through accretion to form solid planets, such as our Earth. In our planet's crust, for example, the most common elements are oxygen, silicon, aluminium, and iron, not hydrogen and helium. Our Earth formed about 4.5 billion years ago, but the very first rocky planets may have formed within 1 billion years or so of the Big Bang. These planets represent new forms of complexity because they contain a much greater diversity of chemical substances than had ever existed before, and that could create even more complex entities, such as the first living organisms.
Hi, I'm John Green. This is Crash Course Big History. Today we're going to be talking about the formation of the solar system approximately 4.567 billion years ago. 4.567. Could that possibly be a coincidence? Yes. So if you weren't asleep during like every minute of grade school, you're probably familiar with the basic layout of the solar system and the 8, formerly 9 planets. What you may not know is how the planets fit between the stars and life as the linchpin of rising complexity.
Mr. Green, what about Pluto?
Oh, me from the past. I know people like to root for the underdog, particularly when the underdog shares a name with Mickey Mouse's dog. Off topic, but how come Mickey Mouse has a dog who is a dog and also a friend, Goofy, who is a dog? But just remember that Pluto also shares a name with the Roman god of the underworld, who was very unlikable. But regardless, the word planet is a man-made classification for a natural phenomenon. We use it because it makes it easier to do science. Pluto hasn't cleared the rocks within its neighborhood orbit like planets usually do, and there's even a dwarf planet on the edge of our solar system, Eris, that's bigger than Pluto. And there are hundreds of others that are comparable to Pluto. The nature of the universe has not changed. It's just that we learned that Pluto was not acting like a planet, so can we please just drop the Pluto thing? So we're now moving from the scale of galaxies, which involve millions of light years, to a neighborhood that's only a few light hours from the Sun to Neptune, the farthest planet, or at most a light year or two to the distant Oort cloud of billions of comets held by the gravity of our Sun. So last episode we talked about how the stars are like our great many times over grandparents. Well, our Sun actually had stars as its parents too. It's most likely a second generation star, which means that the Sun was formed from the wreckage of previous dead stars, and that it contains elements other than just hydrogen and helium, heavier elements that are forged in the bellies of stars, and some of which are like flung out by supernovae. When our star formed, its immense gravitational pull sucked in 99.99% of all the matter in the solar system, so in this case, we are all the 0.01%. But essentially, the rest of the solar system is made up of the debris, like the crumbs, the dregs in the bottom of your coffee cup. Our Sun formed over the course of about 100,000 years in what's called a solar nebula, which is like a fiery cradle of wisps of dust and gas. Then the solar nebula began to compress into a star, probably triggered by a nearby supernova that also, usefully, peppered the solar system with even more heavy elements. And then as the Sun slurped up like almost all the matter in the solar system, pressure made the core of the Sun heat up and it came to life. The usual fusion of hydrogen and helium began to happen and continues to happen, which is nice because otherwise the Earth would be extremely cold and also very dead. So how do we know all of this is true? Well, let's talk to Emily from the Brain Scoop.
Well, a good piece of evidence is the construction site rubble from that time. Meteorites form a sort of fossil record. Meteorites fall to Earth, and some of them are primitive clumps of nebular dust. Careful investigation reveals them to be around 4.568 billion years old. The point is, there can only be 2 environments where iron-60 came from. One is inside a very old giant red star, and the other is within a supernova. Elderly red giants move away from star-forming regions in the galaxy. Chances are the Sun wasn't formed near one of those. So it's much more likely that our sun's formation was triggered by a supernova blast.
So in the early days, the heat from the sun blasted lots of gassy materials away from the inner regions of the solar system, encompassing Mercury, Venus, Earth, and Mars. Further out, in the vicinity of where Jupiter is now, it was cold enough for volatile gases to hang around and even become liquids or solids. That's why the inner planets, like us, are rocky, and the outer planets, Jupiter, Saturn, Uranus, and Neptune, are all these humongous gas giants. So what happened to the remaining 0.01% of our solar system, and what does this have to do with the rise of complexity? Well, the dust floating around the baby solar system wasn't just elements. Like heating in the stellar nebula allowed this dust to sometimes form more complex configurations of elements, like for one thing, around 60 different kinds of minerals. So then the dust began to stick together. Why do I have balloons, by the way? Well, obviously I'm going to tell you shortly. So you may have noticed that if you rub a balloon onto your head for long enough, it will stick. That's because of electrostatic forces, precisely the same forces that allowed the dust in the solar system to gently collide and stick together. And then as those clumps of dust got bigger and bigger, the collisions ceased to be so gentle. So within 100,000 years, there were many objects of up to 10 kilometers in diameter in the solar system, and the force and heat of those violent collisions allowed the formation of still more celestial bodies. Objects continued to collide, the larger objects sucking in the smaller ones with their gravitational nets, and then the largest in each orbit began bulldozing its way through the remaining material. So after about 1 million years, the solar system consisted of a few dozen or so protoplanets. They were roughly between the size of Mars and our moon, and then over the next 10 to 100 million years, the game of pool continued, each collision being something terrifying to behold, until we wound up with the 8 massive planets we are familiar with today. But of course, there's more than just planets in our solar system. There's an asteroid belt between Mars and Jupiter, for instance, which may be a failed planet messed up by Jupiter's gigantic gravitational pull. And then on the edge of the solar system, there's the Kuiper belt, a region of planetary shrapnel like poor old Pluto, and even further out in the boonies, there is the Oort cloud. It's like this huge borderland teeming with billions of comets, but it's still within the sun's gravitational pull, and the Oort cloud is a light year away. That's how massive our sun is, and it's a pretty modest-sized star. So this was a pretty intense time in terms of energy transference. Like all those protoplanets smashing together converted huge amounts of kinetic energy to heat. In fact, it was so much heat that when combined with the heat put off by radioactive materials in the early solar system, the Earth was a molten ball of lava. Basically, the entire planet was as hot as Houston, Texas. What's that? Apparently, it was much hotter than Houston, Texas. Anyway, the Earth underwent a process of differentiation, whereby heavy elements sank to the center and many lighter elements floated to the surface. A lot of the metallic elements, like iron and nickel, sank through the hot sludge to the core, where they still are, and the lighter silicates floated upward, forming the Earth's mantle, a region about 3,000 kilometers thick. The even lighter silicates floated to the surface, where they eventually cooled into the Earth's crust, about 35 kilometers thick in some places, and at the bottom of the deepest oceans, about as thin as 7 kilometers. You can think of the crust as like the thin layer of skin that forms on a bowl of hot clam chowder, and you wouldn't be far from the truth. By the way, I could use some delicious geological clam chowder right now, just like my mom used to make, but with more nickel. The lightest materials of all, including gases like hydrogen, helium, methane, water vapor, nitrogen, ammonia, hydrogen sulfide, they bubbled to the surface and were kind of belched out of volcanoes to form the early atmosphere of the Earth, the steam off the soup. And then even more water vapor was brought in by comets falling to Earth, which we appreciate comets, but even though we do have a water shortage, we don't need you to come back. Much of the methane and hydrogen sulfide in the early atmosphere was converted into carbon dioxide, which turned the sky into like a terrifying red rather than our friendly blue of today. So basically, you've got an Earth with a red sky, volcanoes that are thousands of feet high, a black, barren, rocky surface, the foul smell of sulfur everywhere, scalding hot steam, constant collisions of fire and brimstone from above, occasionally splitting the crust open and creating entire oceans of lava. That's why we call this period in Earth's history the Hadean era, after Hades, the Greek god god of the underworld. But a couple nice things about this crazy, terrifying ball of fire. One, we weren't there, so it's not bothering us. Two, all of this intense heat and pressure allowed mineral combinations to increase dramatically. In fact, there were a whopping 1,500 different combinations, and that would only increase as plate tectonics and life got involved. So during this terrible toddler phase for the Earth, a Mars-sized object dubbed Theia collided with the newly formed Earth in a vigorous kind of body check, or I guess more of a planet check. This knocked out a huge chunk of the Earth's materials, and then over time, those materials accreted into, you guessed it, the moon. The moon, of course, is best known today for inspiring the "moons over my hammy sandwich" at Denny's, but it also inspired the space race and millions of poems and paintings, and it also created tides. But putting aside the tides, which are admittedly a pretty big deal, without the moon, what would wolves howl at in all of those t-shirts? Alright, so as the Earth cooled, the water vapor that had accumulated in the atmosphere fell in torrential rains, like downpours that lasted millions of years. It was like Seattle, but instead of like coffee and grunge music, there was just ammonia. These downpours created the first oceans. Like, as the Earth's surface cooled below 100 degrees Celsius, water vapor was able to stay in liquid form, and somewhere between 3.8 and 4 billion years ago, we had oceans.
Let's talk about food again. This time, though, instead of Earth chowder, let's imagine the Earth as an egg. The crust is as thin as the eggshell. It's also brittle and fractured into segments called plates. Essentially, these plates float on top of squishy, goopy rocks that are close to their melting point. As a result, the surface of the Earth has a history of its own, including the creation of mountains, the explosion of volcanoes, the forging of mighty supercontinents like Rodinia and Pangaea. Plate tectonics affects everything from the movement of continents to the distribution and evolution of species, and is one of the most vital principles of modern geology. It's also responsible for less fun things like massive earthquakes and supervolcanic eruptions that have caused the deaths and even total extinction of millions of species. Finally, the point should be raised that of all the possible scenarios that might kill off the human race, provided we don't kill off ourselves, a supervolcanic eruption is among the foremost of them. In fact, on the scale of millions of years, a devastating eruption is almost guaranteed to happen. And unlike an asteroid, one can't go all Bruce Willis and blow up a super eruption with a nuke. If we're still around, it'll be interesting to see how we cope. Throughout the birth of the sun and the origins of the Earth, there was the chance formation of Goldilocks conditions for life. Like with the porridge and beds that a fairy tale sociopathic blonde pilfered from a baby bear in a break-and-enter job, the conditions for life on Earth were just right. This includes the placement of the planet relative to the sun. The right chemicals were present on Earth to produce the first building blocks for life. More on that next time. Even plate tectonics were hugely important. First, they suck biotic waste, dead things, excrement, underground instead of remaining on the surface. If not for plate tectonics, we'd be more or less swimming in our own you-know-what. Over millions of years, this biotic waste can be transformed into coal or even diamonds. Plate tectonics! We turn your poo into diamonds. And if it wasn't for oceans and plate tectonics, there's a good chance that we'd have the same runaway greenhouse effect that Venus has, where the surface is hot enough to melt lead. Plate tectonics were also crucial to human history. The gigantic landmass of Afro-Eurasia made trade networks possible, which facilitated the exchange of knowledge and technologies, along with sharing diseases to gradually build immunities, something that would be grave news for the isolated inhabitants of North and South America. The distribution of copper, iron, silver, and gold influenced the growth and prosperity of countless societies. Even the distribution of coal beds in Wales was a major ingredient for the Industrial Revolution kicking off in Great Britain. All these things, formed within the slimmest of margins of probability, were Goldilocks conditions for the rise of complexity in the later story. The sustenance of life, the distribution of resources, and even the coal needed for the Industrial Revolution, which exploded into the tremendous rise of complexity in modern times. It's a transformation that continues to this very day.
So speaking of Goldilocks conditions, knowing about the formation of our solar system and the conditions on Earth that were necessary for life is crucial to thinking about the possibility of life elsewhere. The first so-called exoplanet was discovered by Swiss astronomers in 1995, and in 2002 alone, 31 new exoplanets were discovered by independent astronomers. NASA has taken this several steps further. In 2009, they launched the Kepler probe to look at about 150,000 solar systems in the nearby galaxy. As of now, they've found hundreds and hundreds of confirmed planets with thousands more potential candidates. And estimates are that in the entire Milky Way galaxy, there could be as many as 40 billion Earth-sized planets orbiting their stars in the Goldilocks zones for life. And that's just in our galaxy. There are hundreds of billions of galaxies in the universe. Now, I'm not going to tell you that creating life is as easy as shooting fish in a barrel, but if you put 100 trillion bullets in that barrel, you are bound to hit a fish. But given the vast amount of space between solar systems and the fraction of time in which life, to speak nothing of the sliver of time so-called intelligent life, has existed on our planet, we may never encounter other life forms. But I find it tremendously exciting as well as kind of comforting knowing that there may well be other forms of life out there, even if we never run into them, from microbes to multi-celled organisms like, you know, us. Maybe they're as astonished by their existence as we are by ours, and thinking about that, one begins to feel a little bit better about our tiny role in the cosmic play. We may never meet, but we're comrades in the strange phenomenon of rising complexity in the universe. More on that next time. I'll see you then.
Imagine you're in a time machine and you've traveled back 4.5 billion years. And what you're doing is you're taking a stroll on the early Earth. Now, what would it be like? And would you be having fun? Well, the answer is, I don't think you'd be having much fun. First, you'd be walking on molten lava. Not nice. Secondly, you couldn't breathe because there's no oxygen. You'd be asphyxiating. And thirdly, you'd be ducking asteroids and meteorites that are crashing into the early Earth, lots and lots of them. And fourth, you'd probably be throwing up because of very high levels of radiation. And if you stayed there too long, your hair would start falling out too. So I don't think you want to stay there too long. Why was the early Earth so hot? Because that's the main thing, it was really, really hot. Now you've already got some clues as to why it was so hot. And you might be able to think this through. But let me give you 3 of the main reasons. First, do you remember that supernova that blew up just before the solar system was formed? That created huge amounts of radioactive material, and that radioactivity generated a lot of heat. Today, a lot of it's dissipated, so today's Earth is nothing like as radioactive as it was 4.5 billion years ago. Secondly, you remember the process of accretion, really violent, lots of space debris crashing into other space debris. Each collision with a meteorite or an asteroid created huge amounts of heat. And the third problem is subtler because it's pressure. You remember those clouds that the early stars formed from? Well, as the clouds got denser, you remember the pressure increased and they got hotter. And the same thing happens with the early Earth. As it accreted, it got larger, pressure built up and heat built up, particularly at the center. So that's why the early Earth was so hot. In fact, the early Earth got so hot, it melted. And that is really important, because if it hadn't melted, today's Earth would be very different from the way it was. To get a sense of what happened and why this was so important, let's imagine a kind of absurd experiment. Okay, so you're going to put some stuff in a saucepan. You're going to put in some coins. You're going to put in some rice. You're going to put in some plastic. Let's add a bit of mud. Let's put in some ice. And then you can chuck in 1 or 2 other things. And now we're going to heat that stuff up to several thousand degrees. Don't stir. Just let it simmer. Now, it's not going to taste good, but we may be able to learn something from this. And what we'll see is that the whole thing's going to melt. The heavy stuff, such as the coins, are going to sink down to the bottom. Lighter stuff is going to rise to the top, and some stuff is going to evaporate and boil above the saucepan. Now, something very like this seems to have happened to the early Earth. It melted, and because it melted, it formed a series of layers, and they give it its structure today. Let's look at the 4 main layers. Now, the first is at the center. It's the core. It's metallic. Nickel and iron, above all iron, sank to the center of the Earth. And the fact that the center of the Earth is full of metal is really important, because this gave the Earth its magnetic field, and the magnetic field deflects some of the sun's rays that would be harmful to living creatures such as us. So that's the first layer, the core. Secondly, lighter stuff, lighter rocks float above the core and form a layer that's called the mantle. Now the mantle you can think of as a sort of hot sludge of rocks. These rocks are so hot they're sort of semi-molten and they're actually moving around in convection currents inside the mantle. And then at the very top you have a layer called the crust. Very light rocks such as basalts and granites reach the top, they cool, they form this thin layer, the crust. That's where we live. But the crust is pushed around by those convection currents from underneath. You can think of the crust as a tiny thin layer, a bit like a sort of eggshell. And finally, the fourth layer, the atmosphere. Some of the gassy stuff bubbles up to the top, it evaporates. The very light gases, such as hydrogen, disperse into space. But a lot of other gases just hang around the Earth, held by its gravitational pull. And that's how the Earth acquired the structure it has today. All of this happened about 10 million years after the creation of our solar system. Now I want you to hop back in that time machine. And what I want you to do is to take off from your backyard and hover over your hometown. And now I want you to put the time machine into fast motion so it's moving rapidly back through time. And you're going to see something really weird. What you're going to see is that the land is going to start buckling and shaking and moving like a huge monster. This looks weird to us simply because we don't live long enough to see that the Earth is in fact changing all the time. Now in fact, some scholars began to notice this as early as the 16th century when they studied the first world maps that were ever produced. Some of them noticed odd things like the fact that West Africa seems to fit well into Brazil. I mean, look at a modern map and you'll see the same thing. In the early 20th century, a German meteorologist called Alfred Wegener found lots of evidence to suggest that the continents had in fact once been connected. For example, he found very similar geological strata in West Africa and in Brazil. And during World War I, he wrote a book arguing that once all the continents on Earth had been united in a single supercontinent that he called Pangaea, after the Greek goddess Gaia for the Earth. Now, what did the other geologists think of this great idea? They were not impressed. Here's the problem. Wegener came up with heaps of evidence to show that the continents seemed once to have been linked. What he couldn't do was explain how the continents moved around the Earth. So when they said, okay, Alfred, how do you tow a whole continent around the Earth? He couldn't explain it. And as a result of that, his great idea was ignored for almost 40 years. We saw when looking at astronomy that quite often new technologies can generate new evidence which changes our understanding of the science. And something very like this happened in geology. During World War II, sonar technologies were developed to track submarines. And after World War II, some geologists used that technology to try to map the ocean floor. And when they started doing this, they found something that really surprised them. Through many of the Earth's oceans, they found huge chains of volcanoes. And what's happening is that lava is coming up from the mantle, it's rising up, it's forming mountains, and it's pushing apart the old oceanic crust. In the center of the Atlantic Ocean, for example, there's a huge chain of these mountains, and what they're doing is they're pushing the Atlantic apart. So the Atlantic is actually getting wider and wider at about the speed that your fingernails grow. Now, some geologists thought, okay, does this mean that the Earth as a whole is just getting bigger and bigger and bigger like an inflating balloon? But they soon realized that elsewhere in the Earth, crust was going back into the mantle, which balanced what was happening in the Atlantic. Let me explain how it works. Now, to understand this, you need to think of two basic types of crust. There's continental crust, which is the land that we walk on, and then there's oceanic crust, the land beneath the oceans. In general, continental crust is lighter. It tends to be made of granites. Oceanic crust tends to be heavier, made of basalts. Okay? Now, once you've got that, think of two bits of crust colliding, continental and oceanic. What's going to happen? Well, what's going to happen is that the heavier oceanic crust is going to dive beneath the continental crust. Now think of this. It's grinding against the continental crust. It's creating huge friction and lots of heat, and it melts part of the continental crust and punches up whole mountain chains. And that basically is how the Andes mountain chain was formed. Mountains can also form when portions of continental crust collide with each other, but this time, because both portions have about the same density, they don't dive beneath each other, but they crumple up to form huge mountain chains. And that's basically how the Himalayas were formed about 50 million years ago, when India crashed into the mainland of Asia. Now, there's another type of relationship between different parts of crust. Sometimes you get two bits of crust that are moving in opposite directions past each other. What happens is that the friction holds them, but the pressure builds up and then suddenly they slip. This is what's happening along the San Andreas Fault in California, and it's that slippage that creates earthquakes. Okay, these are the basic ideas of the modern theory of plate tectonics. And the theory of plate tectonics is the fundamental idea of modern geology and earth sciences, just as Big Bang cosmology is the fundamental idea of modern astronomy. It explains a huge amount about how the Earth works, just as Big Bang cosmology explains how the universe works. It explains, for example, why all around the Pacific you get a ring of volcanoes and earthquakes. It explains why the Earth is broken up into a series of plates, like a broken eggshell, and why it's around the edge of those plates that you get violent activity such as volcanoes and earthquakes. It explains how mountains form. It explains all the fundamental features of our Earth, and also how the continents move. It explains what Wegener couldn't explain. So the theory of plate tectonics is now the most fundamental idea in modern earth sciences.
That's because it's hard for... Threshold 5 brings us life. What is life? Though there may be many other life forms in the universe, we can only study those that emerged on our planet. So from now on, we focus on our home planet, the Earth. All living things on Earth share important qualities. First, they take in energy from outside to maintain themselves. This is metabolism. Second, they all seem to constantly try to balance the conditions inside and outside themselves in order to survive as long as possible. This is called homeostasis. Third, they can make copies of themselves through reproduction because they all contain huge molecules of DNA or RNA that record how they were made. And fourth, over time, the information in those molecules can change so that later generations may be slightly different. And in this way, living things slowly diversify. Let's consider the ingredients and the Goldilocks conditions needed for life to form. The ingredients are a great variety of complex chemical compounds, including DNA and RNA. Two Goldilocks conditions provide ideal environments for these chemical compounds to combine in many different ways. First, you need energy to fuel those chemical reactions, but not too much, since that would just blast molecules apart. And second, you need a liquid. That's because it's hard for atoms to link up in gases where they are too far apart, or in solids where they can't move very much. So where could we find these Goldilocks conditions? Well, liquids can only exist in a narrow range of temperatures. If the temperature's too high, like right next to a star, then liquids turn into gases. If the temperatures are too cold, like in deep space, liquids turn into solids. Some rocky planets or moons are just the right distance from their suns to have lots of liquid water. They also have the right amount of energy to encourage chemical reactions. Here, on our Earth, 4 billion years ago, you would have found almost perfect conditions for some of the most complex chemistry you can imagine. That chemistry led to life. Let's explore how life has changed and diversified since the emergence of organic molecules and basic cells. One way to view this process is through 6 mini-thresholds. A threshold is a sudden increase in complexity that gives rise to new emergent properties, new qualities. Consider each mini-threshold for yourself. Does it mark something new and different? And if so, why? Our first mini-threshold is photosynthesis. It's likely that the first prokaryotes evolved deep in the ocean near massive vents that provided them with chemical and heat energy. About 3.5 billion years ago, some cells migrated to the ocean surface and evolved to use vastly more abundant energy from the sun. The process they developed to do this is called photosynthesis. It led to an energy bonanza, and that enabled life to spread to many more places. And since oxygen is created as a byproduct of photosynthesis, huge numbers of photosynthesizing prokaryotes over millions of years radically transformed our atmosphere from one rich in carbon dioxide to one richer in oxygen. Oxygen was poisonous for many species, so they died off. But new species emerged that could use oxygen's amazing chemical energy. Mini-threshold 2 is the emergence of eukaryotes about 2.5 billion years ago. These are more complex cells whose DNA is locked up inside a special case called the nucleus, which help protect and preserve vital genetic information. Eukaryotes also contain tiny organs called organelles. Like the organs in your body, they perform special functions such as photosynthesis or processing oxygen. This meant that eukaryotes could thrive in Earth's increasingly oxygen-rich atmosphere, while many prokaryotes perished. That's a pretty important development, since we are made entirely of eukaryotic cells. Around 1 billion years ago, we crossed mini-threshold number 3, the introduction of the first multicellular organisms. In the same way specialized organelles came together to form more complex eukaryotes, different eukaryotes came together to form even more complex life forms. These organisms could contain billions of cells, each with a different function, but all sharing the same DNA. So they worked together. With networks of specialized cells in cooperation, multicelled organisms could respond to changes in the environment in entirely new ways, further developing a key survival trait of life that we call homeostasis. The development of brains is mini-threshold 4. Multicelled organisms needed a way to coordinate all the activities going on inside them, and this became the work of special nerve cells. In some organisms, these cells began to cluster at the head and down the spinal cord to form the first brains. Organisms with brains could process much more information, and they could react to it in even more complex ways, which enabled richer and more sophisticated activities like thinking, and perhaps even consciousness. Mini-threshold number 5 is when life moves from the ocean to land. From about 475 million years ago, some multicellular organisms, beginning with plants and fungi, left the oceans for land. There was a great incentive. This new environment was rich in new opportunities for organisms that could find ways to survive. But that was a challenge, though, as these organisms had to develop special skins to avoid drying out, special ways to breathe out of water, and new ways to reproduce. The modern equivalent would be humans trying to live in space. Mammals, the forerunners of you and me, account for mini-threshold number 6. The first animal to live on land may have been like a modern lungfish, but other land animals soon evolved, such as amphibians, but these still needed to return to the water to reproduce. Then came reptiles, like crocodiles or dinosaurs. These developed large, leathery eggs that could survive well away from water. Then, about 250 million years ago, the first mammals appeared on Earth, evolving from a branch of reptiles that loosely resembled birds. Mammals are warm-blooded, they're furry, and they don't lay eggs. And you and I are mammals. Does the appearance of mammals really count as a mini threshold? Or is it just because we are mammals that we think so? What would be other candidates for mini thresholds, by the way? The development of backbones? The ability to think? Or what about the concept of family?
Hi, I'm John Green, and welcome to Crash Course Big History, where today we are going to get a life, or at least the Earth is going to get a life. But first, today we have to start with a disclaimer. The origin of life is in many ways a blank spot in the pages of history, like the mysteries surrounding the Big Bang or dark matter. The origin of life is still pretty puzzling to us. Like, thanks to scientific research, we have a general idea of what needed to happen to bring about life, but we're pretty fuzzy on the details. Mr. Green, I mean, if we don't know, then why are we studying it as history? Maybe we should just let scientists figure all that stuff out and then they'll get back to us after this class is over. Well, me from the past, I'm sure the thousands of scientists working on that question appreciate your patience, but even when we have blank pages in the annals of history, it's still history. There are still competing ideas and theories about the presidency of Franklin Delano Roosevelt, but the fact that there are open questions doesn't mean it didn't happen. Sometimes we don't have a clear narrative of events, and it's up to us to collect more evidence and refine those theories, but first we have to know about the current evidence and the current theories. I mean, ultimately, that's what history is.
I'm Hank Green, and this is still Crash Course Big History. Last time we left off with a newly born Earth that was molten hot and pelted by asteroids. Then millions of years of torrential rainfall cooled the surface and created the first oceans. We know that life emerged in the oceans between 3.5 and 4 billion years ago. We have solid fossil evidence for life 3.5 billion years ago, and many scientists are pretty confident that life was around 3.8 billion years ago. It's pretty clear that life is a different thing from the rest of the universe, but what makes up that difference? I'm kind of surprised that this turns out to be a super puzzling question that we have yet to come up with a 100% satisfying answer to. But some of the major characteristics of most life are it adapts to the environment, it has a metabolism that processes energy to keep itself going, like humans do with pizza, and it reproduces, whether it be a cell splitting in two or two animals doing their thing in nature. Even these simple criteria have their problems, though. Some animals, like mules, are born unable to have offspring. Some microorganisms can shut down their metabolisms for long stretches of time, but neither are exactly dead or not life. Given the incredible variety of species, definitions for life are by necessity very broad, but one such definition by big historian Fred Spire is, and I quote, "a regime that contains a hereditary program for defining and directing molecular mechanisms that actively extract matter and energy from the environment, with the aid of which matter and energy are converted into building blocks for its own maintenance and, if possible, reproduction." In other words, what makes you different from a star is that while a star burns down till it dies and doesn't actively float around the cosmos looking for more fuel, a living organism does actively seek out pizza to keep itself going, preferably long enough to, have some babies. But how do we know what we know? How do we know that life is just a different kind of molecular mechanism and not something more profound? Well, we can test these claims, and we do, using science. Because life looks so radically different from the inanimate universe, people once thought that life was made of completely different stuff. Then, in 1828, a German chemist, Friedrich Wöhler, used inorganic chemicals to synthesize an organic chemical. This was a big deal. Just as Newton's theory of gravity showed that the heavens and Earth follow the same physical laws, Wöhler's experiment proved that life and non-life follow the same chemical laws, which implied that life could emerge from non-life. Even this idea wasn't completely new. For centuries, the Aristotelian idea that life just spontaneously emerged from non-life was widely believed. For example, if you put some rotten meat out into the sun, eventually the meat would transform itself into maggots. You could probably work out the weaknesses in this theory. 17th century scientists took meat and various other objects thought to spontaneously generate life, boiled them to kill off any eggs previously laid by insects, sealed them in jars, and nothing happened. Oh, Aristotle, first you told us that snot was our brain coming out of our noses, and now you made all those nice people waste their steak dinner. This, however, did not rule out some form of life force in the air. Some invisible force in the Earth's atmosphere that could enter an object and literally breathe life into it. But spores from plants can also travel in the air, as can microorganisms. So in the mid-19th century, Louis Pasteur boiled some organic broth friendly to life and placed it in a flask with a swan neck to trap plant spores and smaller particles. If a life force was in the air, it could enter freely, while spores and other particles would get trapped in the U-bend. And what happened? Nothing. A century and a half later, those flasks are still devoid of life. The conclusion? The ancients were wrong. After a dose of claim testing, it became clear that life must emerge from the inanimate world by chemical processes that are discoverable by science.
But what did early life look like? Well, for a whopping 2.1 billion of the 3.8 billion years of the evolutionary epoch, history was made by tiny single-cell organisms called prokaryotes. That's roughly 55% of the entire story of life. Now, some of those prokaryotes evolved about 1.7 billion years ago into slightly bigger single-celled organisms called eukaryotes, and then, that kept happening and eventually us. But for now, let's just talk about prokaryotes. Prokaryotes lived in the seas and ate chemicals in their surrounding environment. Now, these microscopic prokaryotes might not sound very impressive, but they do make up the vast majority of your family tree. They're also distant relatives of the modern bacteria that are everywhere, crawling around the room that you're in right now, crawling all over you, crawling inside of your intestines. That's right, somewhere right now there is a bacterium that will give you food poisoning in an undercooked hamburger, and it is your cousin. But the thing is, even in its earliest stages, single-cell life was massively complex compared to the inanimate universe. I mean, I know these are tiny little specks, but compared to everything else that had happened on Earth until them, they were an immense tangle of chemical networks and building blocks.
But how did an object as ridiculously complex as a prokaryote first emerge? Well, first of all, it's very difficult to think of how life would form in an oxygen-rich atmosphere like present-day Earth's. Oxygen is kind of a nasty, highly reactive chemical. In fact, if the oxygen levels in this room were substantially higher and I was just rub my hands together really fast, I could burst into flames. And while that would make for a nice viral YouTube video, I would rather not be on fire than get lots of views. 3.8 billion years ago, the free oxygen content of the atmosphere was at negligible levels, which had some not-so-pleasant consequences. For millions upon millions upon millions of years, life dwelt fairly deeply in the ocean, eating chemicals and staying where the Earth's heat kept it warm. Eventually, some prokaryotes floated nearer to the top of the ocean and started using sunlight, water, and the carbon dioxide that was abundant in the Earth's atmosphere to sustain their own complexity using this sweet chemical process they'd come up with called photosynthesis. The waste product of this chemical process is oxygen, and these photosynthesizing prokaryotes pumped a lot of it into the atmosphere. By around 2.5 billion years ago, the amount of free oxygen in the atmosphere was up to about 3%. Oxygen can be nasty, and so scores and scores of tiny single-celled organisms couldn't handle it and died off in a massive wave, sometimes known as the oxygen holocaust. So many species of single-celled organisms, each with the potential to evolve into more complex life, were wiped out. Even at this early stage, our evolutionary ancestors were squeezed through a bottleneck. And this will not be the last such disaster that nearly wiped everything out. Next time you have a bad day, remember that it is amazing that you are alive at all, much less a member of a self-aware species living at the height of human technological progress. Speaking of ancestors, somewhere between 1.6 and 2 billion years ago, the eukaryotes evolved. And because you, your dog, the chicken you ate last week, and the mushroom you ate the week before all descended from them, they really put the you in eukaryotes. And eukaryotes contained organelles, like cellular organs that enhanced their abilities. About 1.5 billion years ago, eukaryotes invented sex. Up until that point, single-celled organisms split in two or cloned with no need to find a partner for romance and DNA exchange. Sexually reproducing eukaryotes possibly obtained these abilities through cannibalism, just eating each other, which may have led to some accidental exchange of DNA. After that, the evolutionary advantages of sex probably resulted in it catching on. Having a partner means having two sets of genes and thus a wider range of genetic diversity from which evolution can pick and choose. Sex is a huge deal. It enhanced evolution and therefore deserves to be classed as one of the most revolutionary advances in the history of life on Earth, and a huge leap forward in the rise of complexity since the very beginning of the universe.
So where did these complex single-celled organisms come from in the first place? Well, Charles Darwin's own hypothesis was that life evolved in some, quote, warm little pond suitable for fostering life. Other scientists postulate that life may have formed from organic chemicals next to the warmth of underwater volcanoes, and still others champion the idea of panspermia, which states that life may have evolved elsewhere in the solar system and then been transported here by an asteroid which seeded the Earth. Like I said, this is a blank spot where many different historical theories are seeking evidence to clarify what happened. It's possible, actually, that this problem could be solved in our lifetimes, which is pretty exciting.
Anyway, whatever physical forces were at play, primitive organic chemicals eventually came together into balls with protective membranes. They would have reproduced and proliferated much as life does today, but the earliest blobs of organic chemicals would have reproduced clumsily, inaccurately, with many useful adaptations getting lost. Essentially, these molecular mechanisms were badly programmed. In the 1950s, James Watson, Francis Crick, Maurice Wilkins, and Rosalind Franklin discovered how living cells replicate using DNA, or deoxyribonucleic acid. DNA is a double-stranded molecule that contains a list of orders for how it wants a living cell to be constructed. And then a single strand, RNA, reads those program orders and sets in motion the production of the proteins necessary to accomplish them. All life on Earth has DNA, which is one of the reasons we know that all living things on Earth, from farmers to fish, from moles to microbes, have a common ancestor. It's why you share 98.4% of your DNA with a chimpanzee, and why you share nearly half of your DNA with the banana that it likes to eat. Not quite cannibalism, but we do eat a lot of our distant cousins. But where did DNA and RNA come from? Another mystery. How could such complex programming evolve from simpler organic forms? One leading contender is the RNA world hypothesis, which postulates that there might have been an earlier version of just RNA, which was capable of both coding and self-replicating, and out of which separate and more complex structures evolved, DNA. DNA and RNA operate in extremely complex ways themselves, which is what you'd expect with something with as many connections and varied building blocks as life. By the way, we're not expecting you to come away from this video with a complete understanding of how DNA works. There is a link in the description to our Crash Course Biology video on DNA, though, if you want this mind-boggling concept to come down a few boggles on the boggle scale. Remember this as well. When looking at a historical narrative, it's always useful to know how things work, but it's still more useful to know why they work, because they can influence the future sequence of events. Like, you don't have to know exactly how to design, build, assemble, and fire a 15th century longbow to understand the French and English conflict in the 100 Years' War. All you need to know is that longbows made things pretty unpleasant for a lot of French people. Like, there's a piece of wood sticking out of me unpleasant. DNA replication is an amazing, flabbergasting process that allows life to copy itself and sustain its own complexity. It copies a living organism with stunning precision. But even this impeccable copying process can occasionally be somewhat peccable. Once every billion copies or so, there is an error. These errors result in a slight mutation. These can have no effect, they could be very good, or they could be very bad. If useful, it allows an organism to be more successful and likely to pass on its genes. If not so useful, things go poorly, and the gene does not get passed on. On the scale of millions of years, these copying errors are the engine of evolution and the origin of new species. They allow the tiny layer of fragile organic material sitting atop the hulking geological structures of the Earth to be shaped and reshaped like Play-Doh, from prokaryotes to eukaryotes to trilobites to dinosaurs to Abraham Lincoln. As Charles Darwin put it at the end of The Origin of Species, there is a grandeur in this view of life, with its several powers having been originally breathed into a few forms or into one, and that, whilst this planet has gone cycling on according to the fixed law of gravity, from so simple a beginning, endless forms most beautiful and most wonderful have been and are being evolved. More on that next time.
Let's try a kind of everything we've looked at has one quality in common. It's not alive. Now, and for the rest of this course, we're going to be looking at things that are alive, at living organisms. Biologists suspect that the universe is crawling with life, that there's life all through the universe, but the truth is we just don't know. The only place we know for sure that life exists is here on our Earth. So that's where we have to study it. Now, what is life? What makes life so distinctive? We all probably feel intuitively that we know what makes life different, but pinning it down precisely is actually very difficult indeed. Let's try a kind of crude comparison. Let's compare two big things. Let's compare an elephant and the Earth. Now, we could say the elephant moves, but we've seen that the Earth is kind of dynamic too. Or we could say the elephant grows. Well, even the young Earth sort of grew during the process of accretion. Or perhaps we could say that the elephant, like all living things, acts with a sort of purpose. Here I suspect we're getting nearer to the truth, but it's still hard to pin down for certain. What we can do is we can list some qualities that all living things seem to have. And in what follows, I'm going to describe 4 key qualities that all living things seem to possess. The first quality we call metabolism. All living organisms are made from cells. All cells can metabolize. And what we mean by that is that they can take in energy and materials from the outside world in order to maintain themselves and keep themselves going. Now, this complicated process is governed by instructions that are contained in the master molecule DNA, that's deoxyribonucleic acid, that is present in all cells. The second quality we call homeostasis. It's a complicated word, but it's worth getting on top of. By homeostasis, we mean the ability of all cells, and in fact all living organisms, to keep constantly adjusting to tiny changes in their environment using the energy and materials they get through metabolism. And homeostasis is also governed ultimately by instructions that you can find in the DNA. The third crucial quality is reproduction. However good they are at homeostasis, eventually all cells, all living organisms break down and die. But it's here that life's come up with a really clever trick for preserving itself. Even when the individual dies, before it dies, it can make copies of itself and its DNA and scatter those copies around it. So the individual may die, but the copies will survive. And that's reproduction. The fourth quality we call adaptation. Over many generations, species can slowly change and adapt and diversify as environments change. The way they do this is actually strangely through mistakes in the copying of DNA. Just occasionally, DNA makes mistakes, but the copy works. And when that happens, and you get a new version that can actually do all these things, it can metabolize, it can do homeostasis, it can reproduce, we say that a new species has been created. It's almost as if DNA was slowly learning how to make new species that can do new things in new environments. And that's how we get the huge diversity of life all around us today. Metabolism, homeostasis, reproduction, and adaptation seem to reinforce each other. They sort of go together. Metabolism provides the energy and materials needed for the constant tiny adjustments of homeostasis and also for reproduction. What adaptation does is allow species to make large adaptations, large changes over time as environments change. And that's the key to evolution. Homeostasis and adaptation together explain why life always seems purposeful, because it's as if it's pushing back somehow against the environment. Now, as far as we know, only living things are capable of combining all of these four qualities. So what is it that holds them together, that links them? The answer is the astonishing molecule that we call DNA. You've seen already that DNA seems to play a crucial role in all the four qualities that we suggested may define life. How does it work, and how is it formed? Well, the best way of thinking about DNA is to think of it as being a bit like the software in your computer. DNA contains the instructions needed to make the proteins that go into the cell and do the crucial work needed to keep the cell going. And it also contains the information needed for DNA to reproduce and for the whole cell to reproduce. How's it constructed and how does it work? Well, DNA is a vast molecule with billions of atoms in it. And they're organized in two great chains. Each chain has arms, and those arms link up to form like the rungs of a ladder. So the whole thing ends up looking like a ladder. Then it twists on itself to form a double helix, and that folds up compactly at the center of the cell. But this is how it works. The information is contained on the arms of the ladder in a special 4-letter code. Molecules inside the cell approach the DNA, unzip the crucial part, read off the code, and then go back into the cell and make the proteins necessary to do what the DNA needs it to do. DNA can also copy itself. This is how that works. The two parts of the ladder separate, and each of the arms goes off into the sludge of chemicals around it and finds its counterpart until eventually you have two identical double strands of DNA. And that's how DNA copies itself, and that's the basis of reproduction in all living organisms. DNA is at the center of our modern understanding of how life works. But even in the 19th century, the English naturalist Charles Darwin had generated a broad understanding of how these changes occur, of how life evolves. Before Darwin's time, most naturalists believed that species were fixed. They didn't change over time. But some had studied fossils, and that seemed to mean that species actually did change over time. The question was, how? That was the question that Darwin tried to tackle. Now, Darwin knew that animal breeders can actually change species quite quickly within just a few generations. And the way they do it is by choosing which individuals will breed and which won't. So if you want to breed fat sheep, you let the fat sheep breed and you don't let the thin sheep breed. And by doing that, quite quickly, you can really change an animal or a species. Now, what Darwin noticed is that something very similar seems to happen in the natural world. It's almost as if nature itself selects which individuals will breed and which won't. Think, for example, of an eagle. Think of an eagle with really good eyesight. It's going to get plenty of food, it's going to reproduce. And think of another eagle that has very poor eyesight. It's going to really struggle, and its chances of reproducing are rather poor. So what this means is that the eagle with really good eyesight is likely to have many more offspring, and slowly over time, its qualities will become more and more common, and that particular group of birds is going to change and become more like the eagle with good eyesight. Now, repeated many, many times over thousands or millions of generations, this, Darwin realized, is the mechanism that changes life. Nature is selecting which individuals will breed. He called this mechanism natural selection. And he figured out that it's the key to the evolution of life. Evolution, it turns out, is a never-ending process because the environment keeps changing, so species keep changing. There's no end to it at all. Now, when Darwin first came out with his theory, it was received with considerable skepticism in 19th century Britain. He actually came up with lots of evidence, but not quite enough, and some things he really didn't understand. For example, he hadn't a clue about the role of DNA. But since then, a lot of new evidence has come to make his theory much, much more powerful. Until today, it's the dominant idea in modern biology. Now, we encourage you to study the evidence. First, look at the evidence available to Darwin, and the best way of doing that is to read his wonderful book, The Origin of Species. It's very readable. It's a classic. It's really worth looking at. And then look at the evidence that's kicked in since then. Now, it's really worth doing this because Darwin's idea and coupled with our modern ideas about how DNA works, are really the key to understanding life and how it works.
Hi, I'm John Green. Welcome to Crash Course Big History. Today we're going to be traversing the evolutionary epic, the great story of magnificent beasts, terrifying predators, quite a lot of extinctions, and countless varieties of evolutionary forms. It's the ultimate epic, millions upon millions of species playing out a drama that has so far lasted 3.8 billion years, with 99% of the actors having already left the stage forever. Then you thought finding employment in this job market was tough. You've already won the lottery, my friend. The keystone of our story is evolution by natural selection. So in the 1830s, a young Charles Darwin traveled around the world on the HMS Beagle. Inarguably, by the way, the most important beagle of all time. I apologize, Snoopy, but it's true. Darwin had the rare and amazing opportunity to study a great variety of the world's wildlife, and upon returning to England, he discovered that a variety of finches he had collected on the Galapagos Islands had beaks that were subtly adapted to their different environments and food sources. Darwin later combined this idea with the observation of how populations tend to overbreed and strain their resources. I mean, if there's competition for resources in an environment, then animals with useful traits would survive and pass those traits on to their offspring. Those who didn't survive long enough to reproduce would have their traits wiped out from the evolutionary tree. Natural selection. We talked some on Crash Course Big History about good science, and Darwin was a good scientist. He worked on his ideas for 2 decades, systematically finding new evidence to support his case, and then finally in 1859 he published On the Origin of Species, and it sent shockwaves around the world. The book offered an explanation for why so many species that seemed perfectly adapted to their environment could have been formed by a blind but elegant law of nature. Darwin's theory was so elegant yet so effective that his colleague Thomas Huxley exclaimed, "How extremely stupid not to have thought of that." Side note, if you ever read On the Origin of Species, try to get a first edition, because in later editions Darwin made a bunch of revisions in answer to some critics, but he got it actually more right the first time. Speaking of which, one of the phrases only included in the later editions and commonly attributed to Darwin was survival of the fittest, but that phrase was actually coined by Herbert Spencer, father of the more troubling social Darwinism, which tried to apply nature's rather harsh laws to human social orders.
I prefer Darwin's original phrase, natural selection. Everything from cuckoo birds that lay their eggs in the nests of other birds, to giraffes whose long necks are good for reaching food in high trees, to humans whose brains make up for their fragile bodies, are selected for naturally. An even better phrase, though, would be non-random selection, or maybe even non-random elimination. While all genetic mutations are generated by a random copying error or random variation completely beyond the animal's control, the selection of those traits is not random. Successful variations that allow you to survive and reproduce are determined by the very specific circumstances of your environment, where elimination, death, might not be far away. So the selection of your traits is done by a very specific and sometimes brutal list of criteria. This is why people who say that they don't understand how all animals could have evolved by chance don't really understand how evolution works. Here's another phrase that doesn't get it right. Evolution is just a theory. In everyday speech, theory means guess. But in science, a theory is something that was tested time and time again, explains many different observations, and is backed up by a mountain of evidence. Evolution is a theory like gravity is a theory, and you don't go jumping out your window because gravity is just a theory. Why are we so certain? Emily knows.
Evolution is one of the most tested, most utilized, and widely accepted theories in science. It's backed up by literal tons of fossil evidence, which can show us shared traits with species that no longer exist and help us map out lines of descent for creatures around today. DNA sequencing further tells us about lines of descent, and you can measure the commonality of the DNA possessed by 2 animals to tell how closely related they are and when they may have split off from a common ancestor. Radiometric dating allows us to assign dates to various fossils, further helping us map out lines of descent. Then there's the simple fact that extinct species are always found in the same rock layers you'd expect to find find them, which is why you don't see a bunny skeleton in Cambrian rock layers from 500 million years ago. That's also how we know that Dimetrodon is not a dinosaur. Closely related species are often geographically distributed near one another. That's not to mention that we can see evolution happening before our very eyes, whether it be the discovery of a new species that recently moved into a different environment, the development of newly adapted bacteria into superbugs, the evolution of new breeds of rapidly reproducing insects, or the almost constant changes in gene distribution in animal populations all over the world.
So, remember the prokaryotes and the eukaryotes? Gradually, some single-celled eukaryotes began to work together in a thing called symbiosis, where one cell did something in exchange for another cell doing something else, thus aiding the survival of both. Some eukaryotes became so cooperative and even interwoven that one cell could not possibly live without the other. Symbiosis was particularly handy in times of disaster. Around 650 million years ago, the Earth was completely frozen over. Snowball Earth was not a great place for life. Many underwater bacteria survived under the ice in oceans. Photosynthesizers may have survived in small hotspots where there was liquid water. In such constrained conditions, it's likely that individual cells started to work together more and more. Now is where we start to blaze through the evolutionary epic of complex multicellular life. Between the start of complex multicellular life and today, there have been 5 mass extinction events. In nature, species compete in niches. It's also called niches, depending on where you're from, but I call them niches. Is an area of the environment that requires a special set of skills and traits to extract food and reproduce. When niches are full, competition is heavy, traits become finely tuned, and evolution generally slows down a little. But when a disastrous extinction event wipes out the majority of the animals living in a niche, the surviving species have room and a lack of competitors to evolve new traits very fast to fill the niche again in what we call an adaptive radiation. The evolutionary epic is dotted with periods of niches filling up, being swept clean by disaster and filling again by new rapidly evolving species. Example, for the longest time dinosaurs ruled the earth and mammals were a puny, timid race of small shrew-like creatures that stayed out of their way. Sometimes we burrowed in the ground or only came out at night or confined our diet to tiny bugs. We could not compete with dinosaurs in their niches. Then the dinosaurs were wiped out and mammals were able to rapidly fill all the empty niches, creating apes and elephants and horses and even whales.
So after Snowball Earth, the Ediacaran era gives us the first extensive fossil evidence for multicellular organisms. They were various ancient forms that resembled today's worms, corals, mollusks, various underwater plants. But then in the Cambrian era, adaptive radiation really got underway and multicellular life filled thousands upon thousands of niches unlocked by their new traits. A lot more is just possible for multi-celled organisms than for single-celled ones. Like, not to brag or to bring up my astonishing strength again, but I can bench much more than a eukaryote. Some of the most famous creatures that got their start in the Cambrian were trilobites, these bug-like creatures with exoskeletons that existed in a variety of species and forms, occasionally in swarms of thousands. And they didn't go extinct for nearly 300 million years. That's over 1,000 times longer than Homo sapiens have been on the planet. Also, as my 4-year-old son can tell you, the Cambrian era had predators like Anomalocaris, which reached sizes of nearly 1 meter long with razor-sharp teeth and grasping limbs. By the time of the Ordovician period, photosynthesizers were making their first tentative steps out of the sea into a new niche, the land. Plants colonized coastlines first, and then gradually, over millions and millions of years, moved further and further inland. In the oceans, life continued to be abundant, with fish and sharks multiplying into a variety of forms. And there were all kinds of crazy life forms, like underwater scorpions that were 2.5 meters long. I mean, for the first 100 million years of complex evolution, a mind-boggling diversity of creatures was emerging. But that also meant all the niches on the planet were getting very full, and many competitors in the same niche made it difficult for a new species to enter it with ease. And then came extinction. I feel like extinction is going to be a thing, Stan. Is there any way we can make a thing for extinction? Yes! Ordovician Earth went through first a major freezing period, killing off many warm water species, and then a radical heating period, killing off many cold water species. Many ecological niches were swept clean, and this removal of competition meant that new species could enter empty niches and evolve rapidly in one of those adaptive radiations. There was also incentive to move out of the seas and onto the land.
In the Silurian period, one of those groups that evolved rapidly by filling terrestrial niches was the arthropods, those exoskeleton species and the ancestors of many of today's bugs. Since plants continued to colonize the land and more of the Earth's surface was becoming forested, that increase in the number of photosynthesizers increased the percentage of oxygen in the atmosphere to between 30 and 35%. Today, it's approximately 21%. Arthropods came out of the sea, started filling niches on land, and their metabolism took advantage of this all-you-can-respire oxygen buffet, growing to enormous sizes like a dragonfly with a meter-long wingspan or a scorpion 1.8 meters long. Again with the scorpions! In the early Devonian period, the forests of the Earth were composed of mosses, ferns, and short shrubs. Some plants eventually evolved a woody covering, which provided some back support and allowed them to grow taller and taller and compete with others in their niche by grasping higher and higher for sunlight. In the first episode, we did promise to explain the existence of trees. Bingo! Also by the Devonian, our vertebrate ancestors had arrived on land. Unlike arthropods, vertebrate skeletons are on the inside, and our skin is more porous, making it easier for water to escape. This limited our ability to fill land-based niches at first. We were amphibious. From this amphibious ancestor, all tetrapods gained their characteristic skeletal structure: 4 limbs, 5 digits. And then once again, extinction. Scientists debate about what caused the Devonian extinction, but once again, a couple of sharp rises and disappearances from the fossil record shows that the niches were being swept clean. Again, the number of species on the Earth drastically declined, but only temporarily.
The Carboniferous intensified the forestation of the planet even more. Meanwhile, amphibians were filling up coastal niches with competition. So to escape into new niches, some evolved less porous skin to venture further inland without drying out, and they also laid eggs with a protective shell, meaning that they didn't have to return to the water to hatch their young. These were reptiles. They were able to fill up the inland world where real estate was cheap, and come to think of it, real estate still is cheap. Next up was the Permian. Many of the forests dried out, creating deserts. Reptiles thrived in this transformed environment with less competition from the forest and river dwellers. Also during this time, the ancestor of mammals evolved. I'm talking, of course, about the synapsids. So considering that they were the ancestors of everything from you to your dog to elephants and whales, it gives you an idea of how radically things can change in just 250 million years of evolution. Because then, once again, at the end of the Permian era, we have extinction. Often referred to as the Great Dying, it was the single largest extinction event of the past 500 million years. Its cause is still debated, but the most dominant theory is an environmental disaster caused by volcanoes in Siberia. All told, over 90% of marine life and 70% of terrestrial life, maybe more, died out. Synapsids were hard hit, leaving space for a huge adaptive radiation of giant reptiles. And now we are finally closing in on my son Henry's favorite period of history, the giant reptile period. In the subsequent Triassic period, the Earth's climate was ludicrously dry with many deserts, and then near the North and South poles it was warm and wet. Again, dry climates were a big win for reptiles, and our mammalian ancestors got a bit of the short end of the stick because there was so much reptilian competition in many niches, so we hit on the fringes. Meanwhile, there were many kinds of giant reptiles in the Triassic, of which the dinosaurs were just one kind until extinction. The Triassic extinction, possibly due to volcanic super eruptions or an asteroid impact, emptied a lot of niches of competition and allowed one particular group of giant reptiles, the dinosaurs, to reign supreme. And that finally led to those periods that are what most people think of when they hear the word paleontology or the word fossil, the Jurassic and Cretaceous periods.
I'll spare you the snarky commentary about how the T-Rex in Jurassic Park actually lived in the Cretaceous. Dinosaurs were the dominant animals on this planet for a whopping 135 million years. That's 540 times longer than our species has even existed. To help you understand this, consider two of the most iconic dinosaurs, Stegosaurus and T-Rex. Stegosaurus was around in the late Jurassic, T-Rex was around in the late Cretaceous. They are separated by roughly 88 million years. Humans and T-Rex are separated by less time than T-Rex and Stegosaurus. Approximately 65 million years ago, the reign of the dinosaurs ends, you guessed it, in extinction. A rock roughly 10 kilometers across crashed into the present-day Yucatan Peninsula with 1 million times more force than all the nuclear arsenals of the world combined. Bad for the dinosaurs, but it opened up a lot of niches previously occupied by them. Many small mammals were able to survive by burrowing or simply requiring less food. They were then in a position for another adaptive radiation. Small mammals quickly evolved into an immense variety of larger forms. And so was the story of complex life on on Earth during the evolutionary epoch. Next week, we will explore the nascent beginnings of a new phase of complexity, the accumulation of more knowledge generation after generation, and the intensification of a newfangled evolutionary invention, culture. See you next time.
I think most people are fascinated by murder mysteries. Well, about 30 years ago, I stumbled onto a great murder mystery. And the victims were the dinosaurs. And the question was, what had caused them to become extinct? Well, I was working on a different project in Italy at the time and sort of stumbled on the level in the rock record where the dinosaurs became extinct. Only there weren't any dinosaurs. There were tiny little single-celled organisms called forams. This is a piece of our beautiful pink limestone from Italy. And if you look really closely down here, you can see there are lots of little specks about the size of sand grains. And those are forams, single-celled fossils, or fossils of single-celled organisms, that almost became extinct at the same time the dinosaurs did. And here's what it looks like in a piece of rock in the field. So this is the last bed of the Cretaceous, which is the time that the dinosaurs were around. And if you look closely again, you can see those little sand-sized specks, which are microfossils. This is the first bed of the Tertiary, which is the time that was after the dinosaur extinction and after the almost extinction of the forams, because the ones that you can see with your naked eye became extinct. Up here there are forams, but they're too small to see. And this is a level of clay in between the two. Now, it's hard now because this piece of rock has been encased in plastic. But we got interested in that clay and what it might tell us. And we, as a group here at Berkeley, it was my father, Luis Alvarez, who was a physicist, and I'm the geologist in the group, and Frank Asaro and Helen Michael, who were two nuclear chemists, who could measure elements at extremely low concentrations. And we decided to measure the element iridium, which is a marker for extraterrestrial material. And we had expected to find either no iridium or a very small amount of iridium in that level. But I'll never forget the day that I got a telephone call from Frank. And Frank said, something is wrong. There is far more iridium in this clay than we had been, than any of our ideas would have predicted. Something was wrong, and it turned out to be the clue that led to solving the extinction of the dinosaur murder, but it took quite a while to figure out what that clue meant. And what we finally figured out was that it was telling us that a comet or an asteroid the size of Mount Everest had hit the Earth on a particular day 65 million years ago and caused the extinction not only of dinosaurs and of forams, but of many other different kinds of plants and animals. For example, like this coiled-shelled ammonite. This group also became extinct at that same time. And we gradually came to realize how much energy there is in a very big rock falling from the sky. There would have been enough energy to blow debris and rocks and dust and chunks of things from the impact site all over the entire Earth. And when it landed on the top of the atmosphere, there was so much of it that it would have made the Earth cold and dark for probably months, so that plants would stop growing and animals wouldn't have food, and many groups became extinct. Not all, obviously, because we're still around. Well, this was a catastrophic explanation for the extinction, and that did not sit well with most geologists and paleontologists of the time about 1980, because we were used to thinking of all changes in the Earth's history as being slow and gradual, and this was the exact opposite. So there was a huge debate. It went on for 10 years, from 1980 to 1990. And meanwhile, people looked for other evidence, and they found other evidence of impact, like spherules and shocked quartz. And all that time, all during that 10 years, the big unanswered question was, where was the crater that would have been produced when this comet or asteroid fell from the sky? Finally, in 1991, the great breakthrough took place. We learned about a huge crater below the surface of the Yucatan Peninsula that the Mexican oil geologists had discovered. It's the biggest impact crater that's formed on this planet in the last billion years. And the Mexicans drilled it, and here's what they found. So this is a thin slice out of a circular core, and this is rock that was melted by the heat of impact. And you can tell that it was melted by impact because the mineral grains in it have features that only form with very great shock effects. And so we then had evidence for a giant impact. We could tell that it was approximately the right age, but you couldn't be sure of exactly the right age. So some of us went and looked at other outcrops in other parts of Mexico, and we found the debris from this impact, from this crater, at exactly the level of the extinction, right at the boundary between the Cretaceous and the Tertiary. And so that was the evidence that has convinced almost all geologists and paleontologists that it was indeed an impact that caused the mass extinction. Well, this is a pretty good example of how science works and how geologists and paleontologists figure out what happened in Earth history. You start with some unexpected evidence like the iridium. Then you make up a theory to try to explain it. And then other people get interested and they look for other evidence like spherules and shot quartz. And there's a great debate because that's the way we work these things out in science. And finally, along comes the most convincing evidence of all, in this case the crater, which convinces virtually everyone. And so that's the story of how geologists and paleontologists solved what may have been the greatest murder mystery in all of big history.
The first living organisms appeared on Earth at least 3.5 billion years ago. To us, they would have seemed tiny and insignificant. Yet they were extraordinarily complex compared to anything else that had ever existed. Over the next 3.5 billion years, they would diversify and evolve. About 600 million years ago, some started to combine. Over time, they formed multicellular organisms like trees, mushrooms, frogs, dinosaurs, or even the first small mammals, which probably looked a bit like mice. When the dinosaurs were wiped out by an asteroid, mammals prospered, evolving into a great range of new species. One group lived in trees and ate fruit. They had hands, stereoscopic vision, and unusually large brains. These were our ancestors, the primates. Our own species, Homo sapiens, evolved about 200,000 years ago. Now, we treat the appearance of humans as a new threshold because we would eventually create entirely new forms of complexity. Today, we have become the most important force for change on the Earth's surface. We are the first species in 3.5 billion years that has had such power. What makes us so different? For this threshold, powerful brains are one ingredient, but it's not just a matter of brains. Many other brainy species exist. They include dolphins and chimpanzees and crows. The other critical ingredient was the development of symbolic language. This enabled humans to share their ideas with each other very efficiently. Human communities grew and interacted, creating the perfect conditions for something new. The ability to learn collectively instead of just as individuals. Ideas and knowledge accumulated generation after generation, and human technologies became more and more powerful. As knowledge accumulated over time, our control of resources and the environment increased and accelerated, leading humans towards two new thresholds that would have a huge impact on our planet.
Hi, I'm John Green. Welcome to Crash Course Big History, where today we're going to talk about the Planet of the Apes films. What's that? Apparently those were not documentaries. But there was an evolutionary process that saw primates move out of East Africa and transform the Earth into an actual Planet of the Apes. But the apes are us. And then we made the movie, and then some prequels, and some sequels, and some reboots, and now sequels to the reboots. Man, I can't wait until I get to see the 2018 reboot of this episode of Crash Course Big History. I hear they get James Franco to play me. So we're about halfway through our series, and after 5 episodes involving no humans whatsoever, today we are finally gonna get some people! Mr. Green, why are we already at humanity? I mean, if we're covering 13.8 billion years, shouldn't humanity come in the last, 2 seconds of the last episode? I mean, humans are totally insignificant compared to the vastness of the universe. We should be checking in on how Jupiter's doing. Fair point, me from the past. Jupiter, by the way, still giant and gassy. There's 2 reasons why we focus a little more on humanity in Big History. The selfish reason is that we care about humans in Big History because we are humans. We are naturally curious to figure out where we belong in the huge sequence of events beginning with the Big Bang. Secondly, humans represent a really weird change in the universe. I mean, so far as we know, we are one of the most complex things in the cosmos. Whether you measure complexity in terms of biological and cultural building blocks or networks or connections, I mean, we're kind of amazing. Now I realize that many of our viewers will be offended by our human-centric bias, but humans are amazing. I mean, we invented the internet, and we invented the animated GIF, and we invented Doctor Who, and then we invented Tumblr, a place where all of these things can come together. So 65 million years ago, catastrophe wiped out the dinosaurs, and we saw the adaptive radiation of a tiny shrew-like ancestor of humans that would look more at home like next to a hamster wheel than in your family album. Let's set the stage in the thought bubble. So the slow waltz of plate tectonics continued to pull Eurasia and the Americas apart, expanding the Atlantic Ocean. Primates colonized the Americas and, separated by the vast Atlantic, continued their separate evolution into the New World monkeys, which is not a band name, although it should be. Then, around 45 million years ago, Australia split from Antarctica, and while mammals outcompeted most marsupials in the Americas, except animals like possums, Australia saw an adaptive radiation of marsupials. This, of course, meant that later, about 100,000 years ago, when the Americas were having their share of mammoths and saber-toothed tigers, Australia was having a spell of gigantic kangaroos, marsupial lions, and wombats the size of hippos. Then, somewhere around 40 million years ago, India, which had been floating around the southern oceans as an island, smashed into the Eurasian continent with such force that it created the world's tallest mountain range, the Himalayas. Meanwhile, in Africa, primates continued to evolve, and 25 to 30 million years ago, the line of the apes diverged from the old world monkeys. And no, neither you nor a chimp is a monkey, nor did we evolve from the monkeys that are around today. Those are like our cousins. Moreover, we did not evolve from chimpanzees. The chimpanzee is a cousin as well, not an uncle. We are not more highly evolved than they are. Instead, our lines of descent split off from a common ancestor with chimpanzees about 7 million years ago. Then chimpanzees further split into a separate species, the bonobos. Knowing about this common ancestry tells us a lot about our shared traits with other primates. For instance, we all have fairly large brains relative to our body mass. We have our eyes in the front of our heads from the days when we hung out in trees, and depth perception was an excellent way of telling how far away the next tree branch was so as to prevent us from plummeting to our deaths. And we also have grasping hands to make sure, that you could hold on to the branch in question. Primates also have hierarchies, social orders, whether male or female led, that determine who gets primary access to food, mates, and other benefits.
Thanks, Thought Bubble. So our closest evolutionary cousins, the chimpanzees, can tell us a thing or two about shared behaviors. For one thing, while all primates have a hierarchy of alphas and betas, humans and chimps, who share 98.4% of their DNA, are the most prone to team team up together and launch a revolution against the alpha male. We're also both prone to ganging up, roaming our territory, and beating up unsuspecting foreigners of the same species, and not for direct survival reasons. Chimpanzees have been observed finding a lone chimp male from another group and kicking, hitting, and tearing off bits of his body and then leaving the helpless victim to die of his wounds. And humans definitely bear this stamp of our lowly origin, where indeed the imperfect step-by-step process of evolution made us highly intelligent, but still with prefrontal cortexes too small and adrenal glands maybe too big. Aggression and bloodlust are definitely part of our shared heritage, and looking at more recent human history, does that really surprise anyone? Contrast that behavior for a moment with the more peaceful bonobos, who are female-led, and when a male in a group gets a bit pushy, the females are prone to gang up and teach him a lesson. When it comes to intergroup encounters in the wild, the male bonobos seem tense around strangers at first, until, usually, the females from each group cross over and just have sex with the newcomers, completely diffusing the tension. Talk about make love, not war. Bonobos are hippies. While our common ancestor with chimpanzees around 7 million years ago was more suited to living in forests and seeking refuge from danger by climbing trees, climate change in East Africa made things colder and drier, and many forests were replaced by woodlands and wide open savanna. Life in the savanna meant our ancestors needed to run from predators rather than climbing trees, so our line shifted away from the bow-legged stance reminiscent of chimpanzees and developed bipedalism, where our locomotion came from legs that were straight and forward-facing. There's still some debate about when bipedalism first began, but we know that by the first Australopithecines around 4 million years ago, our evolutionary line was bipedal. This also freed up our hands. Australopithecines were not very tall, standing only just above a meter, or just over 3.5 feet, and had brains only a little bigger than modern chimpanzees. They were largely herbivores with teeth adapted for grinding tough fruits and leaves. Australopithecines may have communicated through gestures and primitive sounds, but their higher larynx meant that they couldn't make the range of sounds required for complex language. There was probably a lot of pointing and grunting going on, kind of like me before 6 a.m. By 2.3 million years ago, Homo habilis arrived on the scene. They weren't much taller than Australopithecines, but they had significantly larger brains, though still a lot smaller than later species. Excitingly, Homo habilis is known to have hit flakes off of stones to use them for cutting. Now, lots of species use tools. For instance, chimpanzees use sticks for fishing termites out of the ground, and they use rock hammers and leaf sponges and branch levers and banana leaf umbrellas. A lot of these skills don't seem to arise spontaneously just because of the intelligence of individuals, but like in the case of termite fishing, chimpanzees pass the information on by imitation. Primate see, primate do. In a way, this social learning is sort of cultural, yet succeeding generations of chimpanzees don't accumulate information, tinker with it, and improve upon it, so that after 100 years, chimpanzees are owners of highly efficient and wealthy termite fishing corporations. Similarly, as impressive as Homo habilis' stoneworking abilities are, we see very little sign of technological improvement over the thousands and thousands of years that habilis existed. Same goes for Homo ergaster erectus, who was around 1.9 million years ago. Homo ergaster erectus had an even bigger brain, was taller, and they even seemed intelligent and adaptable enough to move into different environments across the old world. They may have even begun our first clumsy attempts at fire, which is vital for cooking meat and vegetables, opening up opportunities for more energy and even more brain growth. But still, there's not much sign of technological improvement. Their tools got the job done. If it ain't broke, don't fix it. Yet 1.78 million years ago, we do see Homo ergaster creating a wide new range of teardrop hand axes in Kenya. By 1.5 million years ago, these teardrop axes had rapidly become common and had improved in quality and were shaped with a flat edge into multi-purpose picks, cleavers, and so forth. Archaeologists see this as the first possible sign of tinkering and improvement of technology that may have been transmitted by social learning. A faint glimmer of something new. Why is this important? Well, humans didn't get to where we are because we're super geniuses. It's not like the Xbox One was just invented out of the blue one day. It was an improvement upon the Xbox 360, which was an improvement upon earlier consoles, arcade machines, and computers, and backward onto the dawn of video games. In the same way, we didn't just invent our modern society by sudden inspiration. It's the result of 250,000 years of tinkering and improvement. This is where accumulation matters. It's called collective learning, the ability of a species to retain more information with one generation than is lost by the next. This is what has taken us in a few thousand years from stone tools to rocket engines to being able to have the Crash Course theme song as your ringtone. Progress. If there was collective learning in Homo ergaster, it was very slow and very slight. This may have been due to limitations on communication, abstract thought, group size, or just plain brain power. But over the next 2 million years, things started to pick up. Homo antecessor, Homo heidelbergensis, and the Neanderthals developed the first systematically controlled use of fire in hearths, the first blade tools, the earliest wooden spears, the earliest use of composite tools, where stone was fastened to wood, wood, all before Homo sapiens were ever heard of around 250,000 years ago. Neanderthals even moved into colder climates where they were compelled to invent clothing. They used complex tool manufacture to produce sharp points in scrapers and hand axes and wood handles, and they improved their craft over time. While evolution by natural selection is a sort of learning mechanism that allows a species to adapt generation after generation with a lot of trial and error and death, collective learning allows for tinkering, adaptation, and improvement on a much faster scale with each generation and across generations without waiting for your genes to catch up. Anatomically similar Homo sapiens have been around for about 250,000 years, and throughout that time we've been expanding our toolkit from stone tools to shell fishing to trade and actual fishing, mining, and by 40,000 years ago we had art, including cave images, decorative beads, and other forms of jewelry, and even the world's oldest known musical instruments, flutes carved from mammoth ivory and bird bones. All this stuff came about as a result of collective learning. As long as you have a population of potential innovators who can keep dreaming up new ideas and remembering old ones, and an opportunity for those innovators to pass their ideas on to others, you're likely to have some technological progress. These mechanisms are still working today. We've got over 7 billion potential innovators on this planet and almost instantaneous communication, allowing us to do so many marvelous things, including teach you about big history on the internet.
So life for early humans was pretty good. Like, foraging didn't require particularly long hours. The average workday for a forager was about 6.5 hours. When you compare that to an average of 9.5 hours for a peasant farmer in medieval Europe, or the average of 9 hours for a typical office worker today, foraging seems downright leisurely. Quick aside, I work 30 minutes a day less than a peasant farmer in medieval Europe. That's not progress. Stan, I want more time off. Stan just pointed out that I have a chair, something that peasant farmers in medieval Europe did not enjoy, and I want to say that I'm very grateful for my chair. Thank you for my chair, Stan. Anyway, a forager would go out, hunt or gather, come home, eat, spend time with the family, dance, sing, tell stories. And foragers were also always on the move, which made it less likely that they'd contaminate their water or sit around waiting for a plague to develop. And with their constant walking and their varied diet, foragers were in many ways healthier than the peasants of ancient civilizations. They were also in some ways healthier than us, but we have antibiotics for now, so we live longer. For now. The classical view of foraging life is best expressed by Thomas Hobbes, who wrote, "No arts, no letters, no society, and which is worst of all, continual fear and danger of violent death, and the life of man solitary, poor, nasty, brutish, and short." Except not really. I mean, life for the average person in 12th century France was also a smidge nasty, brutish, and short. And the lack of wealth disparity in foraging cultures may imply greater equality between social rankings and even between the genders, since female gatherers appear to be responsible for the majority of food collected rather than the hunting males. And from that perspective, life was kind of ruined by the advent of agriculture and then later with states. As Jean-Jacques Rousseau said, the first person who, having enclosed a plot of land, took it into his head to say, "This is mine," and found people simple enough to believe him, was the true founder of civil society. What crimes, wars, murders, what miseries and horrors would the human race have been spared had someone pulled up the stakes or filled in the ditch and cried out to his fellow man, "Do not listen to this impostor. You are lost if you forget that the fruits of the earth belong to all and the earth to no one." And thus summarizes one of the great debates in the world of political science. Man, big history discusses everything. Now, it's possible that neither Rousseau nor Hobbes was completely correct, and that, like, private property and agriculture didn't create the glory days or end them. Like, as previously mentioned, all primates have a dominance hierarchy of some kind. Also, you don't need a wealth disparity to drive human beings to hurt each other. Like, surveys of excavated remains from the Paleolithic indicate a murder rate that was possibly as high as 10%. Now, those statistics are still disputed, but despite the relatively short workday, life in the Paleolithic sounds a lot less appealing when you consider the high murder rate and also the occasional infanticide. That's not even to mention the old or disabled people who, when they couldn't keep up anymore, were abandoned to die in the wild. I can't help but feel that I might not have thrived in the Paleolithic, what with my visual impairment and general lack of interest in hunting. Anyway, we call this the Hobbes versus Rousseau debate, and it's still unresolved. I mean, humans may have been corrupted in many ways by society. On the other hand, it's possible a lot of the crimes and follies of human history may just be symptoms of our coping with the bad wiring left to us by evolution. You know, humans are a bit of an obsolete machine. We aren't particularly well suited to the many lifestyle changes that have happened in the past few thousand years, faster than our genes can keep pace with. But how you interpret the lives of early human foragers largely determines your view of history and also the fundamental nature of the human character. Ask yourself which side you sit on. Is humanity fundamentally good and corrupted by technology and modern social orders? Or are we fundamentally flawed and in need of some sort of structure and authority? Or is there some kind of both-and way of addressing the question? Here at Crash Course, we don't have answers, but we are grateful that you're pondering these questions with us. In any case, collective learning was really good for our survival, but then, 74,000 years ago, disaster struck. A super eruption at Mount Toba on the island of Sumatra in present-day Indonesia clouded the skies with ash and cooled the climate. Plants and animals, aka food, died off, and genetic studies showed that this reduced the human population to a few thousand people. So as a result of this, we aren't exactly inbred, but there's more genetic diversity between two of the major groups of chimpanzees in Africa than there is in all of humanity. So this small group heroically recovered and spread out of Africa 64,000 years ago, colonizing diverse environments and continuing to innovate. For 13.8 billion years since the beginning of the universe, complexity had been rising in a powerful crescendo, but in the space of a few millennia, collective learning was about to make things really bonkers. More on that next time.
Humans have been on this planet for about 250,000 years, and for most of that time we lived in Africa. But then soon after 100,000 years ago, humans began to move out of Africa in a series of migrations that took them eventually all over the world. In so doing, humans had to use collective learning to come up with all sorts of adaptive strategies as they moved into environments that they had never experienced before. Today I want to consider this Stone Age with you, this Paleolithic era, by asking 4 questions. Firstly, how did humans survive in the ice ages? Secondly, what do we know about the chronology and geography of these migrations? When did humans leave Africa and where did they go? Thirdly, let me give you some examples of Paleolithic lifeways, how humans actually lived. And finally, let's consider the question of impacts humans had on the environment during the Paleolithic. Firstly, this question of ice ages. Over the last 2 million years or so, the Earth has been subjected to about 20 different ice ages, each lasting around 100,000 years. The last 2 of these occurred during the Paleolithic era, at the very time that humans began to migrate out of Africa. Great ice sheets covered large surfaces of the Earth, and even where there wasn't ice, forests died out, there was frozen tundra and dry deserts. Imagine trying to survive in an ice age, conditions far worse than you can see me standing in right now. The most important adaptive strategy humans came up with was the controlled use of fire. We know from evidence in Africa that humans were probably using fire about 130,000 years ago at the Chlyses River mouth site. Then we've got very good evidence from the Colombo Falls in Zambia of controlled use of fire to cook animals, to harden tools and so on, between about 110 and 60,000 years ago. So fire, critically important adaptation. At the same time, humans came up with much better clothing, with tightly stitched seams, with far more impressive technology, much better spear points and so on. And even more impressively, the ice ages may have driven humans to adapt art. Symbolic art begins to appear on cave walls during the ice ages. And also we assume that complex symbolic language also appeared at this time as an adaptation to these extreme conditions. So in terms of the chronology and geography, we have evidence of humans leaving Africa about 90,000 years ago, 90,000 BP. By 60,000 BP, that means before present, humans are living in East Asia and Southeast Asia. 10,000 years later, they've made ocean crossings across sounds like you can see behind me here to Australia. By 35,000 years ago, humans are living in the Ukraine. And then extraordinarily, humans move into Siberia at the coldest part of the last ice age around 20,000 years ago. These same humans, these mammoth hunters, then made the final great human migration across the Bering Strait land bridge and into the Americas about 15,000 years ago. In terms of Paleolithic lifeways, we lived in very small groups, 10, 20, 30 at the most. We lived as foragers, scavenging fruits, berries, roots, insects, dead animals, and so on from the environment. The use of hunting is somewhat controversial. how sophisticated was human hunting during this period? It's hard to say. A lot of it appears to have been opportunistic, that is, scavenging animals that others had killed, but some of it was clearly very intentional. The Clyces River mouth site again shows us that about 100,000 years ago, humans were driving elands into especially laid traps. 3 examples. The Inuit people learned to use fire inside dwellings made of ice. They constructed sturdy canoes and hunting tools using animal bones, animal hides, and so on. They followed this lifestyle for tens of thousands of years successfully. Humans living in North America came across very hard stone, Folsom points, Clovis points. These were so effective, tied onto a spear shaft, that they're probably responsible for the annihilation of the mammoths and other large mammals in North America. The sand bushmen of the Kalahari, even today, give us some insight into how humans in desert climates survived. The women gathered using very simple digging sticks and bags. The men hunted with very simple bows and arrows with poison tipped on the arrows. 3 examples. These small groups would occasionally get together with other groups to exchange gifts, ideas, marriage partners. In Australia, these gatherings were called corroborees. So a lot more collective learning would go on here. But having said that, even as humans spread across the landscape, populations remain small, there's no increase in densities, and within these small human groups, collective learning was still very slow. In fact, we estimate that humans probably met less than 500 other humans during their lifetime during this long Paleolithic period. The final question is, what impact did these small groups of humans have? The traditional view is that they lived in harmony with nature, but that view is changing. We have evidence from Australia, from Siberia, from North America of fire stick farming, where Aboriginal people set fire to huge tracts of bushland for tens of thousands of years. In so doing, they radically altered the environment of an entire continent, turning much of Australia into a desert, essentially. The other example of human impacts comes from the extinction of large animals. As humans moved into environments where no human had been before, very quickly all the large animals go extinct. Up to 75% of all the large animals in North America go extinct. In Australia, the figure is 85%. So in the Paleolithic era, this era of amazing migrations, we see the extraordinary creativity of humans having both constructive and destructive impacts on the environment. Humans moved all over the planet, used fire, used tools and so on, proved that no environment was beyond them. But the climate and the small size of these human communities meant that the pace of collecting remained slow. Only with the waning of the last ice age and increases in the size of human population densities did humans cross the next level of complexity that comes with agriculture.
The last ice age ended a little over 10,000 years ago. At that point, human communities in different parts of the world began using a range of new technologies to increase the energy and resources they could extract from their environments. We call these new technologies agriculture, and its development is our 7th threshold. What ingredients led to this threshold? Well, first, thanks to collective learning, humans had accumulated vast knowledge about their environments over many generations. Second, by the end of the last ice age, humans had also settled all parts of the world, and some began to live in denser communities. Populations increased, and some regions, such as Mesopotamia, began to have about as many people as foraging techniques could support. Now, more people meant you had to try to get more food from a given area. So some groups started using simple forms of irrigation, or they planted wheat, or they herded goats and cattle for their meat. These experiments were the beginning of agriculture. Global climates also got warmer and more stable than ever before. These conditions made it possible to plant and tend crops with some confidence that they would yield abundant harvests. Within a few generations, some plants and even some animals became domesticated or more dependent on humans. And as animals became tastier or more nutritious or more docile, they became more attractive to farmers. Farming took off and began to spread around the world. Agriculture was really a way to increase the amount of the sun's energy that was used by our own species. So humans began changing the plants, the animals, and the landscapes around them so that they could use more and more of the products of photosynthesis. This energy bonanza led to the creation of villages, of cities, and of huge agrarian civilizations. Eventually, an even bigger energy bonanza would steer human history towards threshold number 8, the modern revolution.
In the last unit, we crossed the 7th major threshold of complexity in this course, agriculture. We saw how, from about 10,000 years ago, small agricultural villages began to spread in many different parts of the world. These were in fact some of the most important human communities that have ever existed. Now, at first, that may seem surprising, because when we think of human history, we often think first of the great agrarian civilizations. We think of Rome and its empire, or we think of the great Han capital, Xi'an, and its empire. But without the slow spread of simple farming villages, those agrarian civilizations could never have existed. The real key to understanding agrarian civilizations is increasing complexity. Complexity seems to increase as populations increase. But to support larger populations, you need to be able to get more resources from a given area, particularly more food resources. And that's where farming comes in. Thanks to farming, between 10,000 and 5,000 years ago, human populations seem to have increased from about 5 million to 10 times as much, about 50 millions. A lot of those humans still lived as foragers, but probably by 5,000 years ago, the vast majority of them lived as peasant farmers. Now, within each agrarian area, villages began to bud off, both within the core regions and at their edges. So villages began to spread. And at the same time, farmers began to develop new and more productive ways of farming. They began to farm areas they couldn't farm before, they developed new crops, and they began to develop new and more productive technologies of farming. From about 6,000 years ago, some communities began to find more productive ways of using their domestic animals. Instead of just using them for their meat or skin, which you can only do when you slaughter them, they began to use them for products that they develop while they're still alive, such as their fur or their milk or their draft power. Now, that was a real energy revolution. A human can deliver perhaps 75 watts of power, but a horse or an ox can deliver almost 10 times as much. And using that power to pull plows, some communities began to farm lands that you couldn't possibly farm using just ordinary handheld hoes. And using that power, you could also carry goods in a way that was impossible just for human porters. And finally, these more productive ways of using animals made it possible for so-called pastoral nomads to settle the arid steppelands of Eurasia, traveling nomadically with their herds of livestock. But an even more productive innovation was irrigation. Irrigation is used to farm areas where there's not enough rainfall. If those areas have fertile soils, which a lot of them do, then you can get huge crops through irrigation, particularly if you introduce large-scale, sophisticated irrigation systems with canals and ditches that require a lot of organization. As farming technologies became more complex and more productive, they eventually allowed the creation of larger, more populous and more complex societies, the societies we call agrarian civilizations. This transition seems to have happened first in Mesopotamia, in the lands south of the Fertile Crescent, and also at about the same time along the Nile Valley. In these regions, as villages spread and farming became more productive, eventually there appeared the first really large villages and then towns and cities. In the lands between the great rivers, the Tigris and Euphrates in Mesopotamia, irrigation systems emerged that produced huge crops and supported large populations. And then from about 5,000 years ago, there appeared in the south of Mesopotamia, in the region called Sumer, the first real cities. These had populations up to 50,000 people. They had walled gardens, they had fortifications around them, they had temples, they had palaces, and they had complex irrigation systems. We even have a map of one of them, Nippur. That map was carved in clay about 3,500 years ago. These were the most complex human societies that had ever existed so far. The real key to the creation of cities seems to be the tiny surpluses that peasant farmers produced, particularly as their farming became more productive. What this meant was that it was no longer necessary for everyone to be a farmer. Specialists began to appear, potters and merchants and priests and soldiers. And now something happened that was a bit like something that had happened already 500 or 600 million years earlier with the appearance of the first multi-celled organisms. Individuals got so dependent on each other that they began to need some sort of coordinating mechanism. So potters, for example, needed markets to sell their goods on. Soldiers needed governments that could hire their services. Merchants needed courts to settle disputes. Town dwellers and farmers needed someone to maintain the huge irrigation systems on which they depended. And everyone, frankly, needed someone to organize all of these increasingly complex relationships. As a result, in response to these needs, a class of power brokers appeared. Most of these were men. And what they did was they began to take on the role of coordinating society. In villages, they were probably chosen by those they led who needed someone to do this job. But as power brokers became more powerful and had more resources, eventually they began to hire paid enforcers who could impose their will by force. And now, for the first time, we have true states and true governments. And we also have something else. There has appeared a new type of food chain within human society. Farmers extract resources from the environment, from the biosphere. But above them, there's now a new layer of elite groups who extract resources from the farmers by the threat of force. So now societies develop a whole hierarchy. At the top, there's a small minority of people who are very rich and very powerful, who extract resources from the vast majority of peasants who may make up 90% of society. And in addition, there's always, we find, a small class of menials or slaves at the very bottom of the heap. Agrarian civilizations appeared in many different parts of the world. There were important differences between them. They had different languages, different religious traditions, different artistic traditions, but there were also hugely important similarities. All of them, for example, had big cities. And those cities had what we call monumental architecture, temples, pyramids, palaces. They also had rulers, they had hierarchies, they had tax systems, they had armies, and supporting the whole thing was a large population of peasants, most of whom lived outside the major cities. Agrarian civilizations also had writing, all of them. And this is really important because it seems to have accelerated collective learning. Writing probably originated as a system of accounting as those elites and power brokers who were accumulating more and more resources tried to keep track of their resources. But eventually, the symbols used for accounting could be used to convey all the nuances of everyday languages and generate literatures and history, proper writing. Agrarian civilizations appeared wherever agriculture flourished. So this means it appeared in all the core regions of agriculture, with some interesting exceptions. It didn't appear in Papua New Guinea, probably because the root crops that were grown there could not be stored, and agriculture was not quite productive enough to generate surpluses and support specialists. As we've seen, the first real agrarian civilizations seem to have appeared in Mesopotamia, and along the Nile Valley about 5,000 years ago. Some of these consisted really of little more than cities with surrounding villages, but some were huge, including the first Egyptian state, which covered a vast area along the Nile. By about 4,000 years ago, we have evidence of agrarian civilizations in China and other parts of Asia, including Korea, which is where this folk village is. We get evidence of cities also appearing in other regions, such as Central Asia and in Pakistan along the River Indus. Then, by about 3,000 years ago, we get evidence of huge empires, such as the Assyrian Empire. We get evidence of huge empires in China and also in Egypt. The first real agrarian civilizations in the Americas seem to have appeared about 2,000 years ago, just over 2,000 years ago. By 500 years ago, when Europeans first reached the Americas, the Inca and Aztec empires covered a colossal territory. Agrarian civilizations, like the agrarian technologies on which they were based, slowly evolved, spread, developed, got more complex, more populous over 4,000 years. By 1,000 years ago, it's probable that most humans living on Earth lived within agrarian civilizations, and almost all of them would have been farmers. In the last unit, we crossed the 7th major threshold of complexity in this course, agriculture. We saw how, from about 10,000 years ago, small agricultural villages began to spread in many different parts of the world. These were in fact some of the most important human communities that have ever existed. Now, at first, that may seem surprising, because when we think of human history, we often think first of the great agrarian civilizations. We think of Rome and its empire, or we think of the great Han capital, Xi'an, and its empire. But without the slow spread of simple farming villages, those agrarian civilizations could never have existed. The real key to understanding agrarian civilizations is increasing complexity. Complexity seems to increase as populations increase. But to support larger populations, you need to be able to get more resources from a given area, particularly more food resources. And that's where farming comes in. Thanks to farming, between 10,000 and 5,000 years ago, human populations seem to have increased from about 5 million to 10 times as much, about 50 millions. A lot of those humans still lived as foragers, but probably by 5,000 years ago, the vast majority of them lived as peasant farmers. Now, within each agrarian area, villages began to bud off, both within the core regions and at their edges. So villages began to spread. And at the same time, farmers began to develop new and more productive ways of farming. They began to farm areas they couldn't farm before, they developed new crops, and they began to develop new and more productive technologies of farming. From about 6,000 years ago, some communities began to find more productive ways of using their domestic animals. Instead of just using them for their meat or skin, which you can only do when you slaughter them, they began to use them for products that they develop while they're still alive, such as their fur or their milk or their draft power. Now, that was a real energy revolution. A human can deliver perhaps 75 watts of power, but a horse or an ox can deliver almost 10 times as much. And using that power to pull plows, some communities began to farm lands that you couldn't possibly farm using just ordinary handheld hoes. And using that power, you could also carry goods in a way that was impossible just for human porters. And finally, these more productive ways of using animals made it possible for so-called pastoral nomads to settle the arid steppelands of Eurasia, traveling nomadically with their herds of livestock. But an even more productive innovation was irrigation. Irrigation is used to farm areas where there's not enough rainfall. If those areas have fertile soils, which a lot of them do, then you can get huge crops through irrigation, particularly if you introduce large-scale, sophisticated irrigation systems with canals and ditches that require a lot of organization. As farming technologies became more complex and more productive, they eventually allowed the creation of larger, more populous and more complex societies, the societies we call agrarian civilizations. This transition seems to have happened first in Mesopotamia, in the lands south of the Fertile Crescent, and also at about the same time along the Nile Valley. In these regions, as villages spread and farming became more productive, eventually there appeared the first really large villages and then towns and cities. In the lands between the great rivers, the Tigris and Euphrates in Mesopotamia, irrigation systems emerged that produced huge crops and supported large populations. And then from about 5,000 years ago, there appeared in the south of Mesopotamia, in the region called Sumer, the first real cities. These had populations up to 50,000 people. They had walled gardens, they had fortifications around them, they had temples, they had palaces, and they had complex irrigation systems. We even have a map of one of them, Nippur. That map was carved in clay about 3,500 years ago. These were the most complex human societies that had ever existed so far. The real key to the creation of cities seems to be the tiny surpluses that peasant farmers produced, particularly as their farming became more productive. What this meant was that it was no longer necessary for everyone to be a farmer. Specialists began to appear, potters and merchants and priests and soldiers. And now something happened that was a bit like something that had happened already 500 or 600 million years earlier with the appearance of the first multi-celled organisms. Individuals got so dependent on each other that they began to need some sort of coordinating mechanism. So potters, for example, needed markets to sell their goods on. Soldiers needed governments that could hire their services. Merchants needed courts to settle disputes. Town dwellers and farmers needed someone to maintain the huge irrigation systems on which they depended. And everyone, frankly, needed someone to organize all of these increasingly complex relationships. As a result, in response to these needs, a class of power brokers appeared. Most of these were men. And what they did was they began to take on the role of coordinating society. In villages, they were probably chosen by those they led who needed someone to do this job. But as power brokers became more powerful and had more resources, eventually they began to hire paid enforcers who could impose their will by force. And now, for the first time, we have true states and true governments. And we also have something else. There has appeared a new type of food chain within human society. Farmers extract resources from the environment, from the biosphere. But above them, there's now a new layer of elite groups who extract resources from the farmers by the threat of force. So now societies develop a whole hierarchy. At the top, there's a small minority of people who are very rich and very powerful, who extract resources from the vast majority of peasants who may make up 90% of society. And in addition, there's always, we find, a small class of menials or slaves at the very bottom of the heap. Agrarian civilizations appeared in many different parts of the world. There were important differences between them. They had different languages, different religious traditions, different artistic traditions, but there were also hugely important similarities. All of them, for example, had big cities. And those cities had what we call monumental architecture, temples, pyramids, palaces. They also had rulers, they had hierarchies, they had tax systems, they had armies, and supporting the whole thing was a large population of peasants, most of whom lived outside the major cities. Agrarian civilizations also had writing, all of them. And this is really important because it seems to have accelerated collective learning. Writing probably originated as a system of accounting as those elites and power brokers who were accumulating more and more resources tried to keep track of their resources. But eventually, the symbols used for accounting could be used to convey all the nuances of everyday languages and generate literatures and history, proper writing. Agrarian civilizations appeared wherever agriculture flourished. So this means it appeared in all the core regions of agriculture, with some interesting exceptions. It didn't appear in Papua New Guinea, probably because the root crops that were grown there could not be stored, and agriculture was not quite productive enough to generate surpluses and support specialists. As we've seen, the first real agrarian civilizations seem to have appeared in Mesopotamia and along the Nile Valley about 5,000 years ago. Some of these consisted really of little more than cities with surrounding villages, but some were huge, including the first Egyptian state, which covered a vast area along the Nile. By about 4,000 years ago, we have evidence of agrarian civilizations in China and other parts of Asia, including Korea, which is where this folk village is. We get evidence of cities also appearing in other regions, such as Central Asia and in Pakistan along the river Indus. Then, by about 3,000 years ago, we get evidence of huge empires, such as the Assyrian Empire. We get evidence of huge empires in China and also in Egypt. The first real agrarian civilizations in the Americas seem to have appeared about 2,000 years ago, just over 2,000 years ago. By 500 years ago, when Europeans first reached the Americas, the Inca and Aztec empires covered a colossal territory. Agrarian civilizations, like the agrarian technologies on which they were based, slowly evolved, spread, developed, got more complex, more populous over 4,000 years. By 1,000 years ago, it's probable that most humans living on Earth lived within agrarian civilizations, and almost all of them would have been farmers.
Human civilizations have been wonderfully diverse, with an amazing variety of unique customs, religious practices, social structures, and technologies. These differences are fascinating, but big history teaches us to look at the past differently, to seek out commonalities and identify patterns that unite seemingly unrelated phenomena. Often this produces insights that are even more interesting. One of the most important patterns we see among agricultural civilizations is the need to expand. Many agrarian civilizations grew to control a lot of territory. The Roman Empire at its peak controlled around 2.5 million square miles. The Persians more than 3 million square miles, and the Mongols a whopping 10 million square miles, with an empire stretching across Asia. Though these empires existed in different places and at different times, they shared a strong drive to expand geographically. And when they could no longer grow, their territories shrank, and eventually their civilizations collapsed. So why was geographic expansion so essential to their survival? Maintaining a state was expensive. Increasingly large populations required more infrastructure, more resources, as well as bigger governments and militaries. Ambitious monumental architecture like the pyramids added even more expense. Because land productivity had its limits, and leaders could face rebellion if they tried to squeeze subjects too much with heavy taxation, there were limits to how much states could grow using internal resources. Thus, growth necessitated taking what others had produced rather than trying to increase productivity within the state. During the era of agrarian civilizations, this type of military expansion was common. We see it in civilizations around the world, with the Persians, the Romans, the Chinese dynasties, and with the Aztec and Inca empires in the Americas. Large professional armies required food, weapons, and complex infrastructures like roads, forts, and defensive walls. All this came at great expense, which itself increased the need for expansion. Some military innovations led to inventions that would advance entire civilizations. Iron is a good example. The hard metal was initially used for weapons, but once iron ploughs appeared, crop yields increased, and so did populations. Roads, initially designed to move armies, became important trade routes, and building techniques were refined after the construction of so many walls, forts, and watchtowers. Throughout this era, borders were constantly contested, but there was another side to the interactions that took place. Outposts and border regions often became centres for commercial and technological innovation. This was because different cultural groups connected and many non-military exchanges occurred, intensifying collective learning. We see this accelerated change very clearly in Europe when the Roman Empire splintered into a series of small, competitive states. This increase in commerce and the exchange of ideas drove a transition of power from large agrarian civilizations to these smaller commercial states. The pace of collective learning further intensified. Traditional agrarian civilizations in other parts of the world lost power and in many cases were colonized by these same European states, with dramatic implications for today's world. Empires were shaped less by physical borders and more by spheres of commercial influence. The modern world had begun to take shape.
In the Paleolithic era, exchange networks were tiny, linking hundreds or at most thousands of people, most of whom lived pretty similar lifeways. In the agrarian era, they got much larger as populations grew and as the number of settlements expanded. They also got much more diverse as people began to specialize so they could bring different types of information to the exchange networks. And all of this speeded up processes of collective learning. It's not that people got smarter, it's just that there were more of them, there was more information, and over time they got better at sharing their information. Technologies of communication and transportation, once they improved, also sped up these processes. They magnified the size, the diversity, and the efficiency of networks of exchange. Improvements in technologies of communication did a lot to enhance the power of networks of information exchange. The invention of writing 5,000 years ago was particularly important because what writing did was to lock in information over many generations. Writing explains why we can still read the laws that Hammurabi issued in Babylon 4,000 years ago because he carved them in blocks of stone. More recently, the invention of paper and printing has revolutionized the storage and dissemination of information. In fact, here I am in Cheongju in South Korea, where the first book was printed using movable metal type. It was actually printed in 1377, which is 78 years before Gutenberg built his press in Europe. Improved technologies of transportation also made a huge difference. The use of horses, of oxen and camel to transport people and goods revolutionized both transportation and warfare. And they also allowed pastoral nomads to settle the steppes of Eurasia, creating a huge mobile zone that ran all the way from East Asia to the Mediterranean and allowed a huge movement of people, of ideas and of goods. Meanwhile, in Southeast Asia, new boat-building technologies and new navigational techniques allowed people to start migrating into the Pacific Ocean, until by 1,500 years ago, they had settled most of the islands of the Pacific. And finally, the great empires of Persia and China started developing road systems and courier systems, and those systems provided the most efficient ways of moving information until modern times. In Africa and Eurasia, long-distance trading systems developed. And what they did was they connected regional and local exchange networks. The first of these carried goods, people and ideas by sea from China, around India, to Africa and the Mediterranean, and backwards. The second is known as the Silk Roads. It carried goods, people and ideas by land, connecting China, Central Asia, India, and the Mediterranean world. As a result of these networks, 2,000 years ago, silk was being traded all the way from China through Central Asia to Rome and Egypt. And at the same time, you could find Roman coins all the way from Britain to Vietnam. 1,000 years ago, wealthy Persian consumers could order specially designed porcelains in China and have them transported specially around India to Persia. In the 1400s, a Chinese imperial fleet went to Africa, picked up a giraffe, took it back to Beijing and presented it as a gift to the emperor. And in the same century, a Muslim traveller, Ibn Battuta, travelled all the way from Morocco to Central Asia to India, maybe onto China. And wherever he went, he encountered Muslims. As Ibn Battuta's experiences show, religions also travelled along these exchange networks. Buddhism, for example, travelled from India through Central Asia to China, Korea, and Japan, while Islam travelled from Arabia through Persia to Central Asia to India and Southeast Asia. Technologies also travelled these routes. For example, East Asian techniques of printing, of gunpowder manufacture, and also of paper making travelled through Central Asia to the Mediterranean and to Europe. But diseases also travelled these routes, devastating diseases. We know that 1,800 years ago there were smallpox epidemics in Rome, and almost certainly these were transmitted through the Silk Roads. But worst of all, of course, was the Black Death in the 1400s. This seems to have travelled from China through Central Asia to the Mediterranean and Europe, and wherever it arrived, it decimated populations in the great hub regions of Eurasia. But over time, what these disease exchanges also did was to strengthen immune systems, just as exchanges of ideas strengthen the technologies of the hub regions of Eurasia. But throughout the agrarian era, there was a clear limit to the size, the extent, and the power of these exchange networks. That's because the world was in effect divided into 4 great world zones, between which there was hardly any connection. It's almost as if human history had taken place on 4 separate planets. By far the largest and the oldest of these world zones was the Afro-Eurasian zone. This extended all the way from eastern Siberia to southern Africa. Within this zone, from as early as 4,000 years ago, technologies such as the domestication of animals and the use of metals diffused over wide areas. These technologies had their greatest impact in the hub zones. Those were the zones where there were large populations and very diverse connections. In the Afro-Eurasian world zone, the major hub zones were the Mediterranean and Europe, Mesopotamia and the Muslim world, northern India, and Eastern Asia. The second largest of the world zones was the American zone. This was settled from about 15,000 years ago, but within it there emerged 2 major hub zones with agriculture and agrarian civilizations in Mesoamerica and in the Andes region. These, however, had smaller populations and much smaller and less powerful networks than in Afro-Eurasia. So fewer ideas were exchanged, fewer people, fewer technologies. The third great world zone was the Australasian zone. Here, until very recently, most people, the vast majority of people, lived as foragers, except in the highlands of Papua New Guinea, where there were farming communities. Now this meant that populations were tiny by Afro-Eurasian standards. Exchange networks carried limited amounts of information. But nevertheless, in some areas, innovations accrued, populations began to grow. And it's possible that some societies in this zone were heading like the Natufians 10,000 years earlier towards some form of agriculture. The final world zone was the Pacific. This was settled by mariners from Southeast Asia
from about 3,500 years ago to form what was, at least geographically speaking, by far the largest of the world's zones, and by far the largest exchange network. Some of the islands, such as Tonga and Hawaii, were quite large, and they had quite large societies and chiefdoms. But on the whole, the distances between islands were so vast, populations were so small, that the exchanges of information and goods and technologies were very, very limited, much, much more limited than in the Afro-Eurasian world zone. Exchange networks seem to have worked most efficiently where populations were densest, most diverse, and most interconnected. And that meant, of course, above all, in the great hub regions of the Afro-Eurasian world zone. But even here, throughout the agrarian era, innovation and growth face significant limits. The most critical of those limits seems to be associated with a characteristic pattern of rise and fall of populations that you see in all agrarian civilizations. Here's how it seems to have worked. You get an innovation, say irrigation. It allows populations to rise, and they may rise for several centuries. But then, as the great 19th century scholar Robert Malthus pointed out, there comes a point where populations are rising too fast. They're rising faster than innovation. And at that point, you have too many people to feed. Starvation begins to appear. Famines become more regular. Diseases begin to spread. Governments begin to fight over dwindling resources. And eventually, you face catastrophic calamities like the Black Death in the 1400s. If you look at graphs of population growth in agrarian civilizations, you can see this characteristic pattern of rise and falls that we call Malthusian cycles. You can see it over and over again. Then, quite suddenly, in recent centuries, the pattern seems to vanish. And the reason seems to be that rates of innovation increased so fast that they began to overtake rates of population growth. So here's the question. Why did this happen? Why did collective learning become so powerful in recent centuries? Threshold 8 began about 200 years ago, and we're living in the middle of it. We call it the modern revolution because it created the world we live in today. Some geologists call the modern era the Anthropocene. That's the era in which the Earth came to be dominated by a single species, us. How did we suddenly get to be so powerful? First, we became a global species. After the year 1500, human societies began to link up across the world. This created huge exchange networks in which ideas, technologies, goods, and belief systems could be shared. Because collective learning worked on a larger scale than ever before, innovation speeded up. A second ingredient played a crucial role, our discovery of new sources of energy. The fossil fuels, coal, oil, and natural gas, came from fossilized plants and organisms that had stored the energy from sunlight over hundreds of millions of years. Humans learned how to use that energy to power engines of all kinds. Eventually, we learned how to extract energy from nuclear reactions, like those that drive the sun. Globalization, increased innovation, and new energy sources allowed us to build the largest and most complex societies that had ever existed. Today, billions of people around the world can instantly communicate with each other. With abundant energy, a vast range of new materials from plastics to semiconductors, and an astonishing number of new machines, many humans live better than ever before. However, all of this new complexity has consequences. The energy and the food we produce has to support nearly 7 billion people. That requires a huge portion of the Earth's resources. Human technology and activity is literally transforming the biosphere. We may be powerful, but are we really in charge of our power? What lies ahead for our own species and for the biosphere as a whole?
Hi, I'm John Green. Welcome to Crash Course Big History. Today we're going to look at the modern revolution. Mr. Green, but what does modern even mean? I mean, I know that fax machines and Super Nintendo are modern, but like people used to think that toilets that flushed were modern. That's actually a pretty perceptive question, me from the past. So if we're going to talk about modernity, we should probably define modernity. But first, I have great news. There is a future, me from the past, where video games are so much better than Super Nintendo. In fact, this machine plays 24,000 games, and it's in the office of future you. What were we talking about? Oh, right, modernity. So some historians date the beginning of the modern era with the beginnings of the Industrial Revolution in the 19th century. Some date it to the French Revolution in 1789, some push it further back to 16th and 17th century European colonialism. And some date modernity with the European Renaissance and call anything past the year 1500 early modern. But through a big history lens, all of these are just signs of acceleration in human collective learning, which was already underway and took its first tiny steps in East Africa 250,000 years ago. Then again, it would be silly to call the first human foragers early modern. So for the purposes of today, let's say the early modern period began around 1500 and the modern period around 1750, with an acknowledgement that it's all a little bit arbitrary. And I know what you're wondering, but no, 1750 was several decades before the first flushing toilets.
So last week we looked at how collective learning, which relies on population numbers and connectivity to produce new ideas, grew by leaps and bounds with the introduction of agriculture. By the year 1400, the human population had advanced magnificently, but the world was still divided into 4 isolated world zones: the Americas, Australasia, the Pacific, and Afro-Eurasia. From a big history perspective, what makes the European explorations worthy of a place in an episode called Modern Revolution is that they eventually united all 4 world zones into a global system. An increasingly connected network of potential innovators was great for collective learning. But why do the Europeans feel so motivated to expand? Well, a lot of reasons. One, Ottoman dominance of overland trade routes with Asia, particularly after the conquest of Constantinople in 1453, made Europeans seek alternative routes to the populous and rich lands of the East. 2, European states were fairly small compared to some of the vast empires of Asia and needed to compete for more resources to fuel their almost constant wars. And 3, the fruits of exploration undoubtedly had positive effects, whether it be the many advanced inventions and consumer goods imported from China, or the spices of India and Indonesia, or crops from the Americas. That last one should not be underestimated. Crops like the potato, which earned the nickname ready-made bread because it was easy to prepare, combined with maize and squashes and tomatoes and various yams, allowed farms in Europe to support more people. This was also good for Asia, where those crops were introduced in the 17th century. And let us not forget about the vast amounts of silver that the Spanish acquired from the Americas, or the many cotton, tobacco, and sugar farms that Europeans bolstered their economies with. The unification of the world zones also had many negative effects. For instance, it was terrible for people who worked on those cotton and tobacco and sugar farms. Europeans increasingly relied on African slaves, the first of whom were granted to the Portuguese by African rulers, and then, several centuries of horror ensued, with an incomprehensible number of African slaves dying in the appalling conditions of the Atlantic crossing. Life was also pretty miserable for the slaves that survived the journey and generations of their descendants. Also, because Afro-Eurasia was a modestly connected, thriving cesspool of disease, Europeans had developed many immunities. When they started arriving in the previously isolated Americas in the late 1400s and 1500s, the indigenous inhabitants had no immunity to those diseases. This resulted in one of the most horrific events in human history. A cocktail of various European diseases, most notably smallpox, killed off an estimated 50 million people in the Americas in little over a century. A similar tragedy played itself out in Australia when Europeans started arriving there in the 18th century. Now, along with all this horrific stuff, the unification of the world zones was nevertheless a good thing for collective learning, which would eventually prove our salvation in many ways. And this global system continues to increase in complexity and connectivity today, which is why people can now look at this on their smartphone.
Anyway, the unification of the world zones did not in itself lead to a breakthrough in the way humans harvested matter and energy. The last major shift happened with the arrival of agriculture 10,000 years prior. The colonizing European societies of the 16th, 17th, and 18th centuries remained agrarian. But the explorations did allow for a network of exchange that eventually did lead to a major breakthrough in how humans harnessed more energy and produced more and more cultural complexity. The Industrial Revolution. The Industrial Revolution began in Great Britain, as they'll be happy to tell you, in the 18th century, but it was a global revolution involving collective learning shared across the global system. But a number of innovations that kickstarted industry originated in Britain, like the more intensified use of steam engines or the use of coke to refine metal. Not that coke, yeah, that coke. Also, they invented many textile machines, and Britain had lots of coal, and it was relatively easy to mine. Thank you, trees that died hundreds of millions of years ago. We're gonna turn you into industry and smog. But all those British breakthroughs wouldn't have been possible without a huge global network of trade that supplied raw materials like cotton and that opened new markets where Britain could sell its goods. And it wouldn't have been possible to expand that network of trade in the first place without gunpowder and the compass, which both came from China. The methods of porcelain manufacture that were important to the Industrial Revolution in Britain also came from China via Germany, and the improved methods of farming, which freed up many British farm workers for industrial wage labor in the cities, came from Flanders and the Netherlands. Early designs for steam engines came from 18th century France, and much of the designs for these machines depended on mathematics preserved and transmitted by Islamic and Hindu civilizations. So up until the end of the 18th century, virtually all production in human history was propelled by human or animal muscle power, or else by wind and water power. But it turned out that coal and oil had stored energy from the sun that had built up over hundreds of millions of years. And using those resources dramatically increased the energy that humans could harness. Huge numbers of goods could be produced by factories at relatively low prices, which meant that over many decades, goods that had previously been seen as luxuries by common people were suddenly viewed as necessities. By the 1900s, most Europeans enjoyed a standard of living higher than the kings of the Middle Ages. Coal and oil also allowed mechanization of agriculture, which raised the carrying capacity, increasing the population, and new modes of connectivity, beginning with the telegraph and then later the telephone, increasingly bound the human species together, allowing for swift and rapid exchange of ideas. For 250,000 years, if I wanted to tell someone who lived 100 miles away from me something, it took me days to do so. For the last 100 years, it's taken me seconds.
Because a slight tweak in modes of production in the 18th century and the adoption of fossil fuels led to an explosion of productivity and invention in the 1800s and 1900s, people often compare the Industrial Revolution to the Cambrian explosion about 540 million years ago. Remember, when a new skill or trait opens up new ways or niches to extract energy from the environment, evolutionary change can proceed very quickly. In the Cambrian explosion, that evolutionary change was biological. In the Industrial Revolution, that increased pace of change was cultural. Consider bike design. In the 1800s, there were many different designs for bikes, some of which look amazingly, terrifyingly unsafe. In the beginning of innovations for bicycles, a huge number of designs filled all the available niches. Eventually, those designs started competing with each other, and a few forms won out. You got the road bike and the mountain bike and the BMX bike. Just a little bit different variations of the same thing. Another example is the adaptive radiation of electronics. Take a look at all the stuff you needed in the 1980s to do what your average cell phone can do today, and that was only a few decades ago. Many new ideas sparked an increase in the human standard of living and the complexity of societies in tons of different ways. The explosion of cultural evolution that started 200 years ago has yet to cease. The Cambrian explosion went on for millions of years. The agricultural revolution proceeded for thousands of years. We're still right in the middle of the modern revolution, maybe only at the beginning. The huge shift in human activity and a rise in complexity may continue long after our grandchildren's lifetimes. That is, so long as we don't do something stupid, which, you know, with Homo sapiens is always a distinct possibility. And let's not forget about the rise in complexity that's been happening since the beginning of the universe 13.8 billion years ago. A star is essentially a pile of hydrogen and helium. It's extremely simple. By comparison, a brain that arose via biological evolution is an intricate network of billions of connections and building blocks. Industrial society is an immense, whirring global network of millions upon millions of brains, more closely connected than ever before. The products of this society raised complexity even further. Bottom line is this: if the first part of this series, which looked at the vastness of the universe, made you feel insignificant? Just remember that now, at the tremendous heights of technological progress, humanity is, in terms of networks and building blocks, the most complex system that we know of in the universe. And there's currently no end to the potential for rising complexity in sight.
But this brings us to a long-standing historical question. Why did the Industrial Revolution happen in Britain? Great Britain was certainly uncommonly well positioned. That said, so was China. So why didn't the Industrial Revolution happen in, say, Sung Dynasty China between the 10th and 13th centuries? So we know the two main drivers of collective learning are population numbers and connectivity, and China has had both for a long time. The medieval Chinese had much more advanced agricultural methods than Europe. They paid attention to weeding and growing crops in rows and frequently used tools like the seed drill. And they were doing it all centuries before that stuff was even heard of in Europe. In the 900s, the spread of wet rice farming in southern China raised the carrying capacity even further because rice fields simply produce more food. They are more efficient. Also, rice is easier to prepare than the laborious European process of turning wheat into bread. So during the 10th and 11th centuries, the Chinese population increased from about 50 or 60 million to about 120 million. That's a lot of new innovators. So many, in fact, that Sung China came close to having a modern revolution of its own. I mean, coal was used to manufacture iron. Production increased from 19,000 metric tons per year around 900 CE to 113,000 metric tons by 1200 CE. The Sung Dynasty was the first to invent and harness the power of gunpowder, and then later in the 15th century, Zheng He conducted overseas explorations decades before Columbus. Textile production showed the first ever signs of mechanization in ways similar to the European spinning jenny. But China had dry coal, while the British needed to pump water out of their coal mines in order to mine coal, which led the British to build steam engines.
So why didn't the modern revolution start in China around 1000 CE? Well, it might have been the cultural and political climate and a shift away from innovation and commerce at the end of Song China in 1279. Possibly because they hadn't united the world zones in a network of trade and unified collective learning. And possibly because the right combination of cultural innovations required to launch a Cambrian-style explosion of growth just didn't happen. The point is that collective learning is such a powerful force that from the explosion of the world population from only 6 million people 10,000 years ago to 954 million by the end of the agrarian era, the right combination of ideas that led to the industrial explosion might have happened almost anywhere. So long as there are brains to think and exchange ideas, so long as there are energy flows on the earth, humanity has a tremendous potential for rising complexity. The modern revolution was accompanied by explosive growth in human population. It took 250,000 years for humanity to achieve its first billion people. By 1900, the world's population was 1.6 billion. Today, there are over 7 billion potential innovators who are now connected by the lightning speed of the internet, and collective learning is more powerful than ever. Humans now have unprecedented control and power over the Earth's biosphere, which has prompted some scientists and scholars to claim that the Holocene is over, and we now stand on the threshold of a new era, the Anthropocene. During this age, we may continue to raise complexity in our little pocket of the universe to wondrous new levels, hopefully to the growing benefit of all humans rather than just a privileged few. Thanks to collective learning, our potential is awesome, unless, that is, we hit a wall, like agrarian societies did every few centuries when their population growth outstripped their rates of agricultural innovation. We're now in an era of immense danger, where the modern global system of humanity might exhaust the resources of the earth in the same way that agricultural societies often exhausted the resources of the field. More on that next time.
In the last 500 years, our world has been utterly transformed. At the heart of those transformations was a sharp increase in human control over the resources of the biosphere. You can see this increase very clearly if you look at population figures. In 1500, there were 500 million humans living on Earth. In 1900, just 4 centuries later, there were 1.6 billion humans. And today, early in the 21st century, there are almost 7 billion humans. The changes that made this possible transformed our world and created today's world. At their heart is a sharp increase in rates of innovation. But why did rates of innovation increase so suddenly? That's a question that historians have debated for over a century. It's not a problem we're going to solve right now, but what we can do is look at three of the most crucial factors. The first crucial change was a breakdown in the barriers between the four world zones. This allowed a rapid expansion in the size and diversity of exchange networks, as different regions contributed their own plants, animals, customs, trade goods, ideas to an emerging global network, the first in human history. Between 1519 and 1522, a Portuguese fleet traveled all around the world, the first time that had ever been done. By the 1550s, by the middle of the 16th century, American corn was being grown in China, in parts of China where you couldn't grow rice, and it led to rapid population growth. Other American crops were also being grown in Afro-Eurasia, such as tomatoes, potatoes, and sweet potatoes, and everywhere populations began to rise. Afro-Eurasian crops also moved in the opposite direction, such as sugar and coffee, and so did Afro-Eurasian animals, horses, oxen, sheep, pigs. Actually, horses were really ironic, because horses had originally evolved in the Americas, and it seems that they'd been driven to extinction by the first humans to arrive in the Americas. When the Spaniards brought horses back to the Americas, they would transform the lifeways of those Americans who lived on the North American plains. Diseases also crossed the Atlantic, such as smallpox, and their impact was devastating amongst American populations that lacked any immunity. In fact, the die-off as smallpox arrived in the Americas may have been greater than that was caused by the Black Death in Afro-Eurasia. In the 1570s, silver from a mountain of silver in Potosi, in what is now Bolivia but was then part of the Spanish Empire, began to flow through Mexico and Europe and the Philippines to China, becoming the first global currency. New information also traveled. Information about new lands, new peoples, new customs, new plants, new crops, new stars even new gods. And that gave people entirely new ideas about the world and may have contributed to the scientific revolution. By the 1800s, the Australasian and Pacific world zones were being incorporated within this emerging global system that was now the largest, most diverse, and richest exchange network that had ever existed in human history. The second crucial change was an increase in the importance of commerce and markets. In agrarian civilizations, as we've seen, elites and rulers tended to extract resources through the threat of force. But there were many groups such as merchants or artisans or wage earners who actually had to get revenues on competitive markets. What they did was they sold their goods or their labor or their services on competitive markets. And to succeed on competitive markets, what you have to do is you have to innovate. That means you have to offer better goods, services, or labor than your rivals. That explains why where competitive markets flourish, you tend to get a lot of innovation. And that's why, throughout the agrarian era, trading cities such as Venice or Baghdad tended to be areas where you got much innovation, and so did areas between agrarian civilizations, where goods had to be traded on markets rather than exchanged through the threat of force. After 1500, expanding global networks of exchange increased the importance of commerce and markets everywhere, and they began to transform society. Governments began to realize there were huge sources of revenues available in commerce, and they began to support merchants. This was particularly true in Europe, where governments were constantly at war, constantly looking for new sources of revenue, and where merchants were deeply involved in international trade. But these changes also affected ordinary people, particularly peasants, and particularly in regions where growing populations meant that peasants were short of land. Now what they had to do was find new ways of raising money, and that often meant wage work of various kinds. So peasants too began to enter markets as perhaps weavers or artisans. The third crucial change was the discovery of new sources of energy from fossil fuels. In some regions, such as Britain, there had appeared a shortage of wood, and wood was the main source of energy in the pre-modern world. This prompted a search for new sources of energy, and in the 1700s, some innovators, such as James Watt, began to develop cost-efficient steam engines that could turn the world's vast and largely untapped sources of coal into cheap energy. The steam engine marked the beginnings of an energy revolution that would revolutionize our world. By the early 19th century, steam engines were being used for industrial-scale production of textiles and many other goods. And with the invention of railways and steamships, they began to revolutionize transportation as well. By the late 19th and early 20th century, new innovations such as the creation of the internal combustion engine made it possible to harness the power of two other fossil fuels, oil and natural gas. Never before had so much cheap energy been available. To give some idea of this, here are some statistics. We estimate that in the Paleolithic era, each human used on average something like 2,000 to 3,000 kilocalories of energy a day. That's a little bit more than you need just to survive. With agriculture, the domestication of animals, and the harnessing of wind and water power, that figure may have risen in some regions to perhaps 10 or 12,000 kilocalories a day per person. In the early 21st century, it's estimated that each person is using on average perhaps 200,000 kilocalories of energy a day. And most of it comes from fossil fuels. Now imagine what it would mean if fossil fuels vanished overnight and you had to cut your personal energy budget by 90 or 95%. By the early 19th century, these three factors, the creation of the first global networks of exchange, the expansion in the importance of commerce and markets, and the discovery of fossil fuels, began to transform societies in some parts of the world. Those tended to be regions best placed to benefit from these changes, and they tended to be in Europe and around the North Atlantic seaboard. In some of these regions, societies grew rapidly in wealth and power to create the first truly modern societies. By 1900, industrial methods of production based on fossil fuels had spread to Europe, to North America, to Russia and Japan. Innovations particularly affected the production of textiles, of iron and steel, and of chemicals such as dyes and fertilizers. They also transformed communications and transportation with the creation of railways, of steamships, of the telegraph, of the telephone, and of the radio, and also the introduction of commercial scientific laboratories. All of these processes exchanged or accelerated the exchange of people, of goods, and of ideas. These factors also transformed governments. As governments began to face new managerial challenges in a world increasingly dominated by commerce and markets, no longer was it possible for governments simply to skim off resources from peasants through the threat of force. Now, as increasing numbers of their citizens became wage earners, they had to become managers of markets. During the French and American revolutions, governments began to develop entirely new types of partnerships with their citizens through the creation of elections and the introduction sometimes of compulsory military service. They also began to provide new services such as mass education or banking. All in all, governments became more powerful, more complex, more market-oriented, and much, much wealthier. The Industrial Revolution transformed the international balance of wealth and power. It shifted it right away from the old hub regions of the agrarian era, the Mediterranean, Mesopotamia, India, and East Asia. And it shifted it towards a new hub zone whose center was the North Atlantic region. Other beneficiaries included European settler societies such as the Americas, South Africa, and Australasia. By the late 19th century, early industrializing societies, including Britain, the USA, France, Germany, and then Russia and Japan began to use their growing wealth and modern military technologies, such as ironclad gunships and machine guns, to build powerful armies and eventually to create empires. The newly industrializing societies conquered the old superpowers of India and China. By 1900, India was ruled by Britain, and the Chinese economy was dominated by a consortium of industrialized powers. The Middle East, Southeast Asia, and Africa were also carved up into colonies. By now it was clear that industrialization meant power. So by 1900, the world seemed to be divided into two regions: a smaller, industrial, wealthy, and extremely powerful region, and a much larger, weaker, unindustrialized, and much poorer region. It began to seem as if the main changes of recent centuries, or the main result of those changes, was to create two regions, to benefit one region at the expense of another, to create a rich region and a poor region.
What new forms of complexity will appear at Threshold 9? Of course, we don't know. Threshold 9 will include some things that have never been seen before, with entirely new qualities, just like every other threshold. We know for certain that thresholds 1 to 4 have been crossed throughout the universe. But is it possible that other thresholds may also have been crossed elsewhere? Many astrobiologists argue that life may have been created on billions of other planets. This is because the Goldilocks conditions for Threshold 5 are actually relatively common, particularly on rocky planets orbiting at the right distance from their home stars. And once life starts evolving, it's a pretty good guess that it will eventually form large, multicellular organisms. Some will probably evolve brains and perhaps even improved forms of language, and maybe even the ability to learn collectively. If these speculations are right, there may have been billions of planets with creatures capable of collective learning, and some may have already crossed Threshold 9. Let's imagine what this threshold could be. Maybe it involves humans migrating to other planets and star systems, and once we've got there, we might even meet other creatures capable of collective learning. Or perhaps we'll cross Threshold 9 when artificial intelligence surpasses the creativity of human intelligence. Or maybe Threshold 9 will be the threshold of sustainability. It'll be marked by a more balanced and more complex relationship between humans and the biosphere. We may find ways of curing diseases, of extending lifetimes, and improving the quality of life for future generations. And we could do this while sharing this planet more equitably with the millions of other species that live here too. Imagining what might lie ahead is both fun and important, and who knows, you might even play a role in helping us across the next threshold.